I'll just record on the other computer as well. Give me just a second while I get set up here. All right, hopefully you can all see that. People seeing my screen?
Yes, looks great.
Excellent.
Yep.
All right. So welcome to the 2021 Developer Conference. And like last year, where it's an online conference again, as many of you might have noticed, given you're sitting on the Zoom chat at the moment. And also a huge welcome to everyone who is joining in the live stream. This is the first time we've ever tried to live stream the DevConference. And so it's a bit of an experiment. And feel free to ask questions in the YouTube chat. And hopefully there'll be some of the people who are on the Zoom call be monitoring that chat, and we'll be able to relay questions along. Yeah, so the just to sort of put it in your calendar, we've already booked in the conference for next year. So as many of you know, we normally hold the conference in Canberra around this time of the year. And so we did book it in for this time last year. And then at the last minute, we had to move it online, which was our first ever online conference. And so we've now got it booked in again for the 8th to the 10th of April, 2022 in Canberra. And I can already tell you what we're having for the conference dinner, which is a rather nice pizza place that brings their own, wood-fired pizza oven out on a truck with lots of other extra goodies. And we actually paid for the pizza last year. So we've got a 2-year pizza order prepaid. And so that was done with a great pizza place here in Canberra. So if you can book it into your calendar now, hopefully international flights and things will be all good by April next year. And we'll be able to get a whole bunch of the developers down here to Canberra for a live conference. That's a picture down the bottom there of the conference hotel, and a picture just to the right there of the lake just near the conference, just about a 5-minute walk down from the conference. We've got a lovely lake shore with Lake Burley Griffin. And so I've already got a boat. So for preparing for last year's conference, I bought myself a little sailing boat, which I'm looking forward to Pete Hall when he comes down to Canberra, working with him on setting up that sailing boat and then doing some autonomous sailing around. But I'm hoping a few other people will bring boats and submarines and things, but get walking down to the lake. And of course, we've got a couple of flying sites in Canberra as well for vehicles that need a bit more vertical space instead of the lake. So put that into your calendar, ready for next year. But meanwhile, the conference for this year. So this is the schedule that we have. And most of you would have already seen this schedule. We've got a great lineup of talks and spanning a huge range of ArduPilot development. It's always a bit tricky working out exactly what each of us is going to talk about each year, because there's an awful lot of stuff that's been happening in the last year and is preparing to be worked on for the next few months that isn't in this list. But it still gives you a pretty good idea of the range of development happening at the moment in ArduPilot. And thank you very much to all of the speakers for volunteering to give talks. Good idea, by the way, for those who aren't actually speaking at the time, probably turn off your video. It'd be good to have not too many video distractions. It'd lower the bandwidth a little bit. Thanks very much. So Ian, if you could possibly work out how to turn off video, that'd be great. So you see that we've got now the conference, the speaking times here are actually changed a little bit. If you look at the latest link, you'll see that we've now got Paul starting at 9:30. And in fact, we might start him a bit before then, because it was rather silly when I was making the schedule, I put myself in for a 1-hour welcome. And it's not going to take me an hour to welcome you all. In fact, I've only got one more slide for welcoming you to the conference. So the schedule is quite loose. We will, so we'll be basically, starting up talks when we finish the previous one within each session. The session start times will be accurate. So we've got a total of 6 sessions. We've got a morning session and an evening session in Canberra time each day. So the idea is that the people who are coming in from Europe have a session at a decent time in the Canberra evening session, and those coming in from the United States, for example, will have a good overlap in the morning session. And then we'll have a little bit of a break in between. So time for those in Australia to have lunch, and those in the US to have some dinner. And maybe the Europeans might be able to have some breakfast before they come along to the talks. So feel free to ask questions in the chat. I'd also remind everyone that we've got a couple of chat channels on Discord. So we've got the conference April 2021 chat channel. That channel is only available to the conference attendees. That's partners and dev team members and other special invites. And then we've got the conference chat channel, which is available to anyone in the RGPilot community. And we'll be monitoring those channels for sort of questions and things that come up. And we can reload those questions to the speakers at the end of the talks. So the way it will work with the actual talks themselves, let me see if I can get this to actually, there you go, that should now be going to the next one. There you go. All right, so the way we'll be going with the live streaming, so it's live streamed on YouTube. The link's already out there. The live stream's actually been up for nearly an hour already. We were sort of put it up early to make sure people could get things sorted out. And we've had a bit of a chat about fixed wing tuning with Paul in between. So you're also welcome to share the Zoom link with colleagues within your organizations, but please only share with people you personally know so that we don't get Zoom bombed. Those of you who are on the Zoom call last year know that we shared the link publicly, and that was a bad mistake, and we ended up being Zoom bombed by people posting nasty stuff. So that's why we haven't made the Zoom link publicly available. So please don't share it on any public channels. Only share it to people you know personally, so we don't end up with that problem again. If that does happen, we'll end up just changing the password and doing a new link. So I'll shut down the call if it happens, and we'll do that, or the other possibility, I might just enable the meeting room and then only allow people in as they, with the moderators using the meeting room, which might be a reasonable way around it. So the timing, as I mentioned, is only approximate, and we'll likely start talks a little bit early. So be ready if you're up next for your talk. Generally for questions, we have questions at the end of talks usually, but speakers are very welcome to say that they would welcome questions during the talk. And so, for example, in my talk, I'm very happy to have people chiming in and asking questions. And because our schedule is fairly loose, we don't mind if talks take an extra few minutes because of some questions. So it's not a really strict timing. So feel free to, at least in my talk, feel free to ask questions, and other speakers can let their audience know if they're happy to have questions during the talk, or if they'd prefer to wait till the end of the talk. We will, of course, be recording all of the talks and putting them up on the RGPilot YouTube channel. And many thanks to Louis for volunteering once again to be our video editor. It's greatly appreciated. He did a fantastic job last year on editing all of the videos, and the previous year, in fact. Looking forward to having all those up. And the talks have been a fantastic resource to be able to point people at detailed descriptions of new features. And so that historical archive of our talks has been a very, very valuable resource. I'd also like to say a huge thank you to all of the support that the RGPilot project has had from partners in the last year. And the number of partner companies we've had has been really growing very rapidly in the last year. And I should be able to flick across to our partners page, actually. I'll just leave it there at the moment. But if you have a look on the ArduPilot Partners page, you can see the list of partners, and they really are essential to the support of the project. And it's been fantastic to see so many companies supporting ArduPilot financially. It's been really helping with, we help use that to, of course, fund our servers, but also we've got 2 developers who are funded part-time as support people for the partners. And so the recent growth we've had in partners means we might be able to expand that a bit more and fund more partner support. And it's been a very successful program, and we greatly appreciate that funding support from all of the partners. All right, so any questions at all at the beginning about sort of how the conference works or how it's organized?
I have a question, Tridge.
Sure,
Are you
Tom.
taking questions on the yeah, this is Tom Pittenger. Are you taking questions on the YouTube stream, or how are you taking questions? Is it only the Zoom people?
Questions will be coming in from multiple parts. On the YouTube stream, we'll certainly, I hope that several of the people on the call will monitor the YouTube stream, and I will be when I've got time, but I'm monitoring quite a few different channels because we've got the 2 chat channels on Discord plus the YouTube stream. But I will be having a look there, and when some good questions pop up on the YouTube live stream, I'll transfer them across to the Zoom chat or the Discord, and we'll be able to. I think at the end of the talks, I'll also go and pop into the YouTube and have a look at the questions that have been highlighted there. We'll have to just see how well that works, but we should be able to transfer some of those questions from the live stream across to the speakers so that we get those questions addressed at the end of the talks. But we'll sort of play it by ear a little bit, see how that works. And I think it'll actually work quite well, but you know, we'll see how it goes. We've never tried a live stream before, so we're not quite sure how well that'll work. Any other questions at all about how it's all organized? We're all raring to go and to start up early. All right. Well, if there's no more questions, then I think we might
Andrew,
move on to the first talk. James?
I was going to say, just before we kick off, given we are quite early, we might just give the audience on YouTube a bit of a question and answer session. Just let them ask some questions so we can shape things, and then we'll get stuck into Paul's presentation probably in 15 minutes or so, or if there's no questions sooner.
If there's no questions, actually, we could start it sooner. So let's have a look at that. I'll just need to bring
and to add to that, what would be nice is if we could get some feedback from the audience about what they'd like to hear. Because being that this is the beginning of the conference, it'll be for a while, we could maybe steer it a little bit in different ways, depending on what people want to hear, more in, for emphasis and whatnot.
Yeah, so let me have a look here. So we don't seem to have any questions that I can see right now. So yeah, but all right. So, but feel free to. I'm inclined, if we don't have any questions, soon, I think we should actually kick off the first talk and then have more time for questions after the talks, because I suspect that the talks will actually generate a lot of questions and interest, and it'll give us more opportunity to be able to address those with bits at the end of the talks. And so I'm inclined actually to move on and kick off Paul's talk early. So it'd be about 15 minutes early from, I currently got it scheduled at the 1:30. So if any objections to that, should we kick that off a little bit early and hand over to Paul now? All right, I think we should probably do that. So I will stop sharing my screen there, and let me see how we're going here. I'm going to switch the recording to start recording again for the new talk. So Paul, if you would like to start sharing your screen. So I'll just introduce you. So Dr. Paul Riseborough is the GNC lead for ArduPilot. So he's been working with ArduPilot for many years now, and most well known for his work on the state estimation EKF, but he's the EKF2 and EKF3, in fact, EKF1 as well, which we retired some years ago. And but also works on many other areas of the code, and he's provided really fantastic contributions to the ArduPilot project. So over to you, Paul.
Thank you, Andrew. So welcome everybody. It's just as well that this was put into a morning session because it's got a couple of equations in it and it uses the word physics. So but it's a bit hard to get away from that. So what we're, when I was putting together this talk, initially it was just going to be an overview of the features that we've added. But there was one feature that stood out, and it's one that's actually quite difficult to tune. And I'll switch to the, I'll share my screen now. Okay, that should have gone through. Just give me a thumbs up if you're seeing that.
That's working great, Paul.
Okay, excellent. All right. We've added, I think late last year, we had a pull request was merged that added the ability to do wind estimation to our multi-rotor platforms. And this came up. In fact, I'd like to put out a thanks to Watts Innovations, Bobby Watts, his company that funded this initial implementation. And it was really driven by the observation that for many of our multi-rotor platforms, depending on your direction of flight and the velocity, there's a perturbation in the measured barometric pressure because of the airflow around the fuselage. It can increase or decrease the pressure inside the fuselage or the autopilot. That changes the Barrow height, and you end up with variations in height when accelerating and decelerating. And the way around this with a fixed wing aircraft is you can do a compensation using airspeed and then compensate the Barrow for the effect of the airspeed on the measured pressure. But with multi-rotors, we don't measure airspeed directly, so we have to infer it. And the feature that was added enables the EKF to estimate the airspeed of the aircraft and the wind drift by measuring the drag in the forward and sideways direction. Now, why would we want to have a wind speed estimate? Well, besides the correction for Barrow errors, there are other operational requirements. One could be operating limits for wind, particularly for vehicles operating beyond visual line of sight. It's important for the operator to be able to monitor the wind conditions at the flight location and return home. We can also do better predictions of power required. So in addition to the changes enabling the EKF to estimate the wind drift for the multi-rotors, there were also some changes made to the Barrow libraries, enabling the estimated airspeed to be combined with correction coefficients so that we could correct the Barrow for flight in the forward, backwards, right, left directions. Look, feel free to pop up with questions if you have them along the way. Some of these concepts can be a little bit they are currently complex. I've tried to make them as simple as possible and minimize the number of equations, but because I've strayed into physics in part of this talk, I'll understand that there will be people that come from different backgrounds. So to be able to use the measured accelerational drag on a multi-rotor to estimate wind, we have to have a mathematical model that predicts what the drag would be based on the flight speed. And multi-rotors have two dominant mechanisms that contribute to drag. And the largest one usually by a factor of 3, is what's called rotor momentum drag. And this is unlike normal bluff body drag, which varies with speed squared, like the drag on your car driving along the road, which goes up with speed to the power of 2. Rotor momentum drag is proportional to speed. And for our vehicle types and the flight speeds we operate at, it tends to be the dominant drag term. Fortunately, because rotor lift, thrust from the rotors is in the Z direction for a traditional multi-rotor, it means the forces in that horizontal, that X and Y direction, are pretty much due to the momentum drag and the bluff body drag. So if we have a mathematical model of those drag terms, then we have a basis with an extended Kalman filter for being able to work backwards to estimate the airspeed in that direction, and therefore estimate the wind drift. Okay, so this is where I'm almost certain that there will be questions asked, because this made sense to me when I was putting it together last week. But it does introduce some new concepts. So that's a diagram showing a rotor disc. So just to give you a bit of a heads up, we've got the lift of the rotor, which is obviously in the direction of the rotor shaft. On a multi-rotor, I've made the assumption that the rotors point up, or that they're horizontal. You know, when you get into tilted rotors, this method of wind estimation in the EKF won't work. So if we're flying in the direction of the x-axis, so x is forward on our multi-rotor, y is right, and z is down. So we're flying with an airspeed, and the rotor is, and when we're flying in horizontal flight and we're flying sideways, we have the rotor is sucking air in through the rotor disc, and that's what we call the induced velocity. That's the velocity through the rotor disc caused by the action of the rotor. And as the air goes through the disc, the rotor adds pressure to the air. It doesn't instantaneously accelerate it. That's a common misconception. It adds pressure to the air, and as the air then passes through the disc and goes below it, that pressure then gets converted to kinetic energy, pressure energy to kinetic energy, and that induced velocity reaches a steady state value of 2 times the induced velocity at the rotor, and that acceleration of the velocity is what causes the thrust. And that's what happens for air that's passing perpendicular to the plane of the disc. However, because we don't have an infinitesimally thin rotor disc, we actually have a rotor with blades, and those blades have a projected area when viewed from side on. Some of the airspeed, or some of the speed of the air, tangential to the plane of the disc, and you can see this vector here. Some of that airspeed is lost when the air passes through the disc. And when you think about it, so we've got a mass flow of air. So every second there's so much air that passes through the disc, measured in, you can measure it in kilograms per second. That's mass flow. That mass flow rate multiplied by the change in speed equals a rate of change of momentum. So we can't change. There's been a change in horizontal momentum of the air passing to the rotor disc. You can't change momentum without a force, and that force is momentum drag. Pardon me. Now, what makes momentum drag larger? Well, if you have a larger blade chord or a larger blade pitch, that is more blade area when viewed side on. So if you look at your rotor from side on, and you have a look at the projected area of the blade seen from side on, the larger that area is, the larger the momentum drag is. And an interesting fact, that ducted fans have absolutely huge amounts of momentum drag, because the ducted fan, because it's got a duct, it basically straightens the airflow out. And when the airflow comes out the other side of the duct, it's lost all of its sideways velocity. Multirotors, so we refer to this as a momentum drag coefficient. It's almost like a measure of how much airspeed is, horizontal airspeed is lost going through the propeller disc. For multirotors, that K value is less than 0.1. Now, we've added a parameter to the EKF that represents that momentum drag coefficient, but to make it more intuitive to use, we've scaled it such that it represents the ratio of acceleration to velocity. So that's the first parameter, and the parameter is called EK3 drag MCOEF. And I'll show you shortly how we actually tune that parameter. So that's the most important drag parameter to get right. The next component of drag is what we call bluff body drag. And that's the drag that more people would be familiar with. That's the drag that acts on a car driving down the road. It's the drag, any bluff body moving through the air. And the underlying mechanism is that you've got, if you put a square block or some blunt shape in a wind tunnel and you blow air past it, as the air velocity comes towards the front of that object, it slows down to a stop at a stagnation point. And of course, if you take air and you bring it to rest, then there's a pressure rise, and that pressure rise is half times the density times the velocity squared. And that's the same mechanism that our pitot tubes use on our planes to measure the rise in pressure due to airspeed. And obviously, if you increase the pressure on the front of the object, that's a drag force. And we measure that drag force as that half times density times speed squared, which is also dynamic pressure. And we multiply it by the frontal area and multiply it by a magic number, which represents a drag coefficient, as in how draggy the shape is. And to give you an idea, for non-streamlined shapes like cubes and cylinders and spheres, and the sorts of bluff bodies that we have for our multi-rotor bodies, that value will be somewhere between a 0.5 and a 1.5. And unless you've calculated it, a good value to assume as a starting point is 1. So we can now work out, we can now express the acceleration, which is obviously that drag force divided by mass. And to make setting this parameter easier, because we don't want people to have to set frontal areas and drag coefficients, we've introduced a parameter called a ballistic coefficient. And the ballistic coefficient is really the ratio of the mass to the area times the drag coefficient. And the tuning advice for the parameter is that you measure the frontal area on the vehicle. And I'm going to switch off the screen share now. So here's a small multi-rotor platform. And if you're setting the ballistic coefficient for this particular platform, you take the frontal area, you measure the frontal area, you'd measure the mass of the vehicle, you divide the mass by the frontal area, and that's the ballistic coefficient parameter that needs to go into the EKF parameters. Okay, so we have it's 3 parameters.
So Paul, a couple of questions. So the total contribution of drag from momentum versus bluff body, typically it's more from momentum or more from bluff body?
More from momentum.
It's what sort of ratio?
It's, well, for the logs that I've seen, it's probably a ratio of 3 to 4 to 1.
Right. Now, so it's really mostly momentum drag that matters.
Yeah, we'll see typical flight speeds. Now, what's important is that momentum drag scales with velocity. And bluff body drag scales with velocity squared. So at low speeds, it's nearly all momentum drag.
Mm-hmm.
But if you go fast enough, eventually V squared, because the velocity, because bluff body drag scales with V squared, if you go fast enough, eventually bluff body drag overtakes momentum drag.
Mm-hmm.
But typical flight speeds, 10 up to 15 meters per second, which is where most of our multirotors fly, it's dominated by momentum drag.
Mm-hmm. And Pete Hall had a question on the chat. He was asking, is momentum drag independent of throttle?
No, it is not. It actually does vary with the amount of thrust that's been produced. So effectively, it works, it's proportional to the speed and the momentum, the mass flow rate through the rotor disc, and mass flow rate varies with thrust, the square root of thrust. So, but we make an assumption here that the average, on average, the thrust is equal to the weight. So we could do a scaling with throttle, but throttle isn't a particularly good measure of total thrust because the propellers, depending on the inflow through the propellers can unload. We could actually use, probably a better metric would be a filtered vertical acceleration. So if I was going to make a refinement to this, we could use the filtered Z acceleration and try to, take the square root of that and then apply that as a scaling factor. But in practice, I've found that unnecessary to get this algorithm to work. So we make an assumption that that rotor lift is equal to weight.
Paul, one observation, when we were designing Loiter, we initially just started out with a velocity squared coefficient for drag when we're doing our drag model, because Loiter works off this, a pretend drag that we implement. So, and then we ignore wind. So the idea is Loiter should be all told without wind. And we found when we did that, it felt completely wrong. And that's why we actually came to exactly the same conclusion that you've shown, that the velocity, proportional to velocity relationship felt right when we were doing that. And so that it's nice to actually understand why that was.
Yeah, and it's a very important drag term when you start thinking about where you're going to optimize your vehicle design. So, for sort of lower speeds, up to 15 meters per second, for example, which where most of our multirotors fly, the best way to reduce that drag is actually to put propellers on with slimmer blades, as in, smaller chord blades.
Yep.
But then you lose a bit of hover efficiency. So that's the classic trade-off, cruise efficiency versus still air hover efficiency.
Yeah. Now, the other question I'm sure a lot of people will be wondering right now is with as you change payload weight. A lot of payload-based multirotors might be operating with a 4:1 minimum to maximum payload, minimum maximum takeoff weight state, where they're dropping off. Just before they drop something off, they weigh 4 times more than when they actually fly back. That's probably the most extreme case, but how will this handle because that's obviously going to completely change the velocity, that momentum equation. How will this handle that sort of problem?
Okay, so there will be an error, but the other thing to think about, if the payload's in the vehicle, it also adds to the mass.
Yep.
And this magic ballistic coefficient parameter in the EKF, as I'll explain shortly, is essentially the ratio of the acceleration drag divided by the velocity. So you double the mass, all right? So now your thrust has gone up by a factor of 2. So you've increased the momentum mass flow rate through your propellers to generate the extra lift required.
Yep.
So the drag has gone up, but the mass has gone up. So the drag acceleration doesn't vary by as much as you would think.
Right.
But if you're talking 4-to-1, yes, that's where starting to look at, potentially measuring current draw into the propellers, because with fixed pitch propellers, the current draw into the actual motors, which is actually, you could infer from current draw into ESCs factored by ESC throttle percentage, is probably the best metric of shaft torque on the propeller, and therefore best metric of actual thrust being generated by the propeller.
Yep.
We can probably have a good conversation offline about how we can work that into the system.
Yeah, it was more just an interest. The questions were more along the lines of, are we going to see a massive variation in this prediction, or is it still, or just a significant, but is this parameter something that can be that has to be set and it's fixed, and therefore we'll see it just a constant offset, or is this something that will just be a momentary error in the output that will come back?
Yeah, you'll probably have to work out where the wind estimate is more important to you, right. With the load on or the load off. Yeah. I suspect with the load on. So
again, it's something that could actually be changed during the flight when you drop a parameter, drop a payload off to account for that on the way back.
Absolutely. Too. And if you're talking about payloads, then you really have to start thinking about the bluff body drag as well.
Yeah. Yeah,
we could detect that by the hover throttle changing. If the hover throttle changed significantly, could we do some sort of automatic scaling of these parameters?
Oh, totally. Yeah.
The takeoff thrust, that's one of the things I was thinking too, was that we do actually effectively measure our takeoff weight based on our hover throttle.
Yeah, we'd have to work hover throttle back to, and hover throttle in theory with the scaling that we apply.
Is thrust, it's hover thrust.
Hover thrust, yes.
So yeah, and yeah, so there's definitely so there is a few opportunities there that we could do to, like, without being too clever to actually address that problem. But no, cool.
All right. Okay, so I'll back to the screen share. See if I can. Okay, so we have the 3 parameters, and I've got links in the presentation which will take you to the parameter descriptions. Now, by default, these parameters are 0 and the feature's turned off. In terms of determining the parameters, the momentum coefficient value, I mean, in theory, you can determine it analytically if you have a propeller modeling package. In practice, it's much easier to determine it from a flight test. The ballistic coefficients, you can get close enough just by looking at projected areas and the ratio of mass to projected area. Okay, so what's the tuning process? The first is to do flight data gathering. And that involves a specific set of maneuvers in outhold. Outhold's the recommended mode. And it's best done in low wind conditions. I mean, look, you can do it in high wind conditions. What's more important than the actual wind level is consistent wind. So a late evening or an early morning flight test is preferred when you don't have a lot of convection induced turbulence, as in thermals. The next step is we set the ballistic coefficients. We use the mass and projected area in the X and Y directions. Then there's a log analysis step to determine the momentum drag coefficient. Once that's determined, if the log gathered has been was done with log disarmed 1 and log replay 1, so that enables logging from boot, and it logs all of the messages required to replay the data through the EKF, then we can actually take those tuning parameters, run them through the EKF, and actually check to see that it will give a stable wind estimate. Okay, so what's the flight test sequence? As I said, out-hold mode is the preferred mode. And the reason for that out-hold mode is preferred is because when you release the sticks in out-hold mode, the vehicle goes flat and it holds a constant altitude, and then the velocity is just purely horizontal. So what we're trying to do in this flight test is accelerate the vehicle into the wind, then flatten the vehicle out so it has zero roll and pitch, and then allow it to decelerate where there's no forward thrust from the rotors, and we're just getting the drag on the rotors and the drag on the body, and just naturally decelerate until it comes to a stop and then starts drifting back downwind. Then we allow it to drift back downwind, and while it's drifting downwind, that gives us an accurate measure of our underlying wind drift, which we actually need for the analysis. Then we yaw the vehicle through 90 degrees. Then we accelerate to the left. So then we measure the drag for flight to the left. We repeat the process, measure drag when flying backwards, and then once again repeat the process and measure the drag flying to the right. And that gives us the front, right, left, back measures of drag, and gives us the basis for checking the parameters, and not just the drag. This data will also come in useful when we start to look at the corrections for the barometric errors. So are there any questions on the flight test process? Okay.
So one question actually, Paul. So what's the possibility of us having like an auto tune on this, where we actually, rather than having to analyze the logs and do it that way, of having some way of learning it automatically within the vehicle?
I think that's entirely possible, but I mean, the complicating factor is obviously you've got your upwind. Once you've established the wind drift direction, which we do with the existing auto tune to sort of hold position. I know that it tends to yaw into the wind, yaw so that the tuning axis is, aligned with the wind vector. In theory, we could do the same thing. We could accelerate in a direction, go flat, wait for it to start drifting back to the starting line, then reposition, go forward, rotate. This could be scripted, definitely.
So either a script or just something that even an auto mission that just goes between two waypoints backwards and forwards.
The problem with doing it is that you need to know what the truth value for the airspeed is. That's a problem, and this is why
going in, if it's constant, just going in two directions isn't good enough to say, the average.
No, but the problem is you don't know what the side slip. So in theory, if you had in the controller the ability to yaw the vehicle whilst it was translating between the lines until the side force went to zero, or the longitudinal force went to zero, in theory, you would then be able to work out the wind drift based on a zero side slip assumption.
So weather vaning, essentially.
The weather vaning effect. But in practice, something where you just do a short dash upwind and then drift back is probably going to be more reliable. The only problem is that you need a bit of space to do this test. I mean, I had about 3 meters of second per wind for the flight test I did earlier in the week to gather this data, and I was probably requiring a minimum of about 50 meters of space to do the acceleration and then the drift. And you can see the figure on the presentation. They're 10-meter grids.
Yep. Leonard had a question as well in the chat. Leonard, do you want to give your question now, or shall I?
No, it's all right. I stopped the video again. But the change in area, like a lot of multi-rotors, their central sections are very disc-like. So they've got a very large effective area when looking down upon them, and a much smaller looking horizontally. As you tilt forwards, the effective area and the direction of travel can increase significantly. Are we accounting for that change in effective area versus direction in any way, or are we just sort of taking a median?
Okay, so we're only measuring, because if you have a think about the momentum drag, it's tangential to the propellers, so it's only in the X and Y direction. So any force,
I was more talking about the bluff body drag.
Yeah, but same thing with the bluff body drag. So we actually only use the component of the airspeed in the direction of that axis. So it's component based. Now, look, I realize that anybody that's producing a lift or a negative lift, that bluff body drag. So we are measuring the acceleration in the X direction.
No, yeah, you're answering the question well. That's I think I understand where you're.
So we only look at the
aircraft overcomes the drag from the Z component.
That's right. So in this instance, flying in forward flight like this, we're only measuring the component of force in the direction of that body axis. We don't include the component of force in the Z direction. And
yep.
The other thing, to make sure that we get that right, that's why it's important to do the outhold test, where you make that, we don't look at it during the acceleration phase. We actually do the assessment once we've flattened the vehicle out to 0 roll and pitch, and then we're just doing this sideways translational slide.
Yes, and we're actually deriving something from these measurements as opposed to calculating the total drag on the aircraft. We're actually using the force vectors in the XY to calculate the wind speed. So I'm thinking about that in completely the wrong way. So yes, 100%.
So it is built in the mathematics, but yes, in one sense, you're onto something, because you can't with a like a pancake, like a flying saucer shaped body, for example. If you're getting it to start to generate lift, or by lift I mean downforce, while it's tilted, it's going to actually, that lift, you can't generate that lift without also creating an induced drag component. So there, and also with flow separation. So it will actually have an effect on drag in the X and Y direction, but it's a bit unpredictable.
Yeah, everything's but we're all the first order effects are all solid, but there are going to be
effects,
a number of second and third order effects that add error to our predictions. But that's cool.
All right. Okay, so here's an example with the little multicopter. So I did a very rough, just almost 1 centimeter little blocks or squares to work out what that area was, and came up with an estimate for ballistic coefficient in the X and Y direction. So that's a starting point. And then the next step was to plot the XY acceleration. And if you plot X and Y, IMU acceleration and GPS velocity, then that gives you the basis, with a little bit of head scratching looking at the log, to work out what the airspeed was when you were decelerating to a stop, and then therefore what the ratio of drag acceleration to airspeed is. So here's an example log. This is what you might get. Now, for those of you that don't use Mav Explorer, apologies, but you probably should. Just giving it a plug.
Yay.
Because you can do cool things like apply a mathematical formula. So if you just want to use the absolute value of the acceleration, you can do that. Just build it into the graph. Anyway, we have a handy tutorial, a handy page on our wiki in terms of how to use Mav Explorer. Okay, so here you can see that as the GPS speed goes up, and then you can see also that either the X or Y acceleration goes up. Now we need to zoom in. So here's an event in the flight where we'd accelerated into the wind, nose first, then released the stick, and then the vehicle decelerated. So here's the acceleration phase. And then we release the stick. We get a transient as the vehicle pitches. And then it goes into its, decel and coasts down to a stop. At this point, you can see that the GPS speed goes to 0 and then picks up again. And that's where the vehicle has gone as far upwind as it's going to get. And then it starts to slowly just drift back, accelerate back downwind until it reaches its drifting at the same speed as the wind. And you can look at this graph and then go, well, okay, well, the wind drift is probably in the order of around about 3 meters per second. That is asymptoting too. So hopefully that makes sense what's going on here. Nose into the wind, tilt forward, accelerate. This is at 45 degrees tilt. Very rapid acceleration. Release the stick, a little bit of a transient, then decelerate to a stop with the vehicle level, and then it starts to drift back downwind. You look at this drift period, that's your 3 meters per second wind drift. That means that the actual wind speed here, which was actually 8 points. So here we've got a wind speed of a speed at the point where we start our coast down of 8.8 meters per second, or ground speed. We add 3 meters per second of wind speed to it. So we've got 8.8 ground speed at the point when we start our decel, and it's stabilized. 3 for the wind drift, so we've got 11.8 meters per second of wind. We go down to Excel, and this is where you've got to do a little bit of visual smoothing of this data. It might be handy to low pass filter it. We do have the ability to do that within Mav Explorer. And that's 2.8 meters per second squared. That's the Excel. So now we've got an airspeed and we've got an acceleration due to the drag. But remember, this acceleration is bluff body drag and momentum drag. So we've already worked out a ballistic coefficient. So we take the equation for drag acceleration as a function of ballistic coefficient, which is half times density times speed squared. Then we divide that by the ballistic coefficient. So now we know how much of that acceleration was due to bluff body drag. And that tells us, we subtract that from the total, and that tells us we've got a little bit over 2 meters per second squared is due to momentum drag. So now the calculation to calculate that coefficient becomes fairly simple, and it's simply the momentum drag acceleration divided by the velocity, and that's the magic number that goes into the EKF. And depending on how energetic you're feeling, you can go through and repeat that for the other test points, get a number of data points, and then take the average. So any questions before I go to the next step?
Yeah, I feel as though we're going to need like a screen, like we added the mag fitting thing in Mav Explorer. It brings up a page where you fill in various parameters. Like you could have a box where you enter, what your wind speed was, and then get it to then do that fit across multiple examples. I think automate this process. I think it would make it a little bit less error prone.
Yeah.
Yeah, certainly a bunch of worked examples in the wiki would be really, really good.
Yeah. So anyway, hopefully this log can form a basis for putting some worked examples in. Okay. So, all right, so now we have some parameters. So I've got a momentum coefficient, I've got a ballistic coefficient, and I've got a log that can be replayed. So this is where it starts to, now at this step, for many users, they could probably just stop at this step and then go, all right, it's going to work a lot better than what I had before. Could probably just stop there and go out and flight test it. But if you've got a replayable log, it is actually just worthwhile to become familiar with the replay facility. We do have documentation for it. It's reasonably easy to use. And certainly if you've got a system, I don't know how well we're logging on some of our lower power boards, like the F4s. How are we going with dropouts?
We do get some, but it depends on the quality of the SD card and how much RAM you can basically, if you cut out during the test, you do things like disable terrain following terrain database and a few other things to gain some memory and then put more memory into your logging, you're more likely to be able to get a full log with all of the details. Yeah. So I think it'd be quite doable on an F4, just a little bit more setup. Yeah. And just to explain to people, there's a parameter, I think is log buff size. Log file buff size. So buff size, which sets the amount of RAM that it buffers the log data between writes. And the bigger that is, the better. But you'll probably have to turn some features off. Also, if you're prepared to fly with just one EKF, it can also help just to set the EK3 IMU mask to 1. That also halves the amount of logging as well, or not completely halves it, but significantly reduces. And it gains 20K of RAM, which you can then give to your logging. So certainly if you did that, you could, on pretty much all of our boards, you could then get a good quality replay log, except for the boards that don't have SD cards. Boards without SD cards, this whole system just won't work. Yeah. Okay. Now this is where I switch across to my VM and actually show you an example of how this log file runs. So when you're setting up to do logging, you've got to configure the board type. Oh, yeah, configure. Then you build it for replay, which I've already done. And then this is where we can, hopefully that's showing okay with the VM. Yeah. Which screen are you seeing? You are seeing the VM? Yeah, we're seeing the VM. The font's a little bit small, but most people will be able to read it, I think. Yeah. I know there's a shortcut way to resize that, but I don't remember it. Okay, so now we run the replay. Anyway, while the replay is running, I'll actually show you a log that I've generated previously in the magic of time travel.
Okay, so we've generated a log. So the first item to check, once you've run the replay with the parameters to enable the wind estimation, is we'll plot the GPS speed and we plot the wind estimates. Now, something to remember with replay is that when you replay a log, the replay data is given an instance number for the first lane of 100, second lane of 101, third lane 103. So if you want to plot the replay data, not the original data, then you need to plot the instance 100, ID 100. If you don't do that, you'll become really confused while you're changing your replay parameters and nothing is changing on your output because you're actually plugging the original log data. Okay, so here we go. This is what these are the wind estimates. And you can also graph. So this is how we would check the output. Now, there's a sanity check to be applied when you're replaying the log. And if we go back to the slide, what you're looking for, if you plot the magnitude of the wind speed, right towards the end of the coast period, when the vehicle has essentially reached where its ground speed is essentially asymptoted and reached the speed of the wind drift, you should see that the wind speed is within a metre per second of the actual GPS speed. And that's what we see here. So see where the arrows are. This is where the vehicle is now starting to drift backwards with the wind, and the estimated wind speed and the GPS speed are virtually identical. That's a very good sanity check. The other one is that the wind speed estimates are reasonably stable and that the direction of the wind speed and the magnitude is consistent with the observations on the day. And it's important with the flight test process that you take a note of the direction of the wind. So here's another plot. We can see it was somewhere in the order of 3 meters per second, and it was consistent with the observation that the wind was from the south-southwest. If you're into Kalman filters, you can plot the innovations for the drag. Not very informative as a general rule. There's a method of tuning, which I'm not showing because it's time consuming and it needs to be automated with a script, where you can adjust the tuning parameters and find the parameters that minimize the root sum square of the innovation sequence. That's what that looks like. So before I go on to the section for tuning the Barrow compensation parameters, are there any questions on the log analysis, the EKF replay?
Oh, I was wondering how much variation you see in the coefficients, I guess, or the values that you're tuning for across vehicles, or maybe you haven't tuned enough vehicles yet to know. I'm just wondering. I'm just thinking, it looks like a very complex process, and there's multiple ways to get around that, automation, et cetera. Maybe we can, find coefficients for our well-known vehicles, and it's at that point that I'm thinking of,
Yeah.
if we knew what the a standard 250 quads coefficients were, and then a massive hexcopter delivery drones, what its coefficients are, could people just use those instead of trying to, figure out what they are exactly for their vehicle?
I think that's a really good idea. I think that's entirely feasible. What I've found, okay, so the vehicles I've tuned, the smallest vehicle I've tuned is this. The largest vehicle was I don't know, I think it was in the order of about a 15 kilo heavy lift quad, but something that was optimized for a bit more lift capacity and endurance, not speed. And for the heavy lift quad, the momentum drag coefficient in the EKF was about 0.1, 0.12, and for my little quad here with small propellers, but it's about 0.17, and then for a 3DR Iris, I got something closer to 0.2 for the momentum drag. So that gives you the range. The ballistic coefficient, I'm not so worried about that. That's pretty easy for people to set, in the sense that it's a function of frontal area and the ratio of frontal area and mass. So I think we could probably give somebody a picture from a drone front on, one side on, shaded area, saying measure this area, measure the weight, divide one number by the other. I think that's probably okay.
Cool, thank you very much.
Yeah.
Just a quick question on the area. Is the side-on area of the blades taken included in that measurement?
The side-on area of this, say again?
The side-on measure, the area of the blades take up side-on, which could be a reasonable
no, we don't
portion.
include. Yeah, we don't include the area of the blades. It's just area of everything, because the area of the blades viewed side-on is essentially what contributes to momentum drag.
Yep, cool. Thanks.
Hey, Paul, it's Buzz here.
Yeah.
Quick question about how quickly the wind speed estimates are updated in the real world. Once you've done all the tuning and you're just flying in windy conditions, how well does this system cope with gusts and sudden wind changes?
Well, okay. So I'll share my screen again.
Sorry, I might be getting ahead of you.
No. It's a good. In fact, that wasn't on my list of items, so it's good to bring it up. Okay.
I guess I was just wondering what the time coefficient is with respect to the analysis. How often it is able to make that estimate.
Yeah, well, you can see here. There was a bit of thermal activity. The sun was still up. It was about 4 o'clock in the afternoon, or thereabouts, and still some gusts coming through. And you can see this should probably give you an idea of the sort of filtering that gets applied to the estimate. You can see when it takes off, it thinks there's 0, and it probably achieves a steady state within about a minute after taking off. But then at other places where it takes about 30 seconds to respond to a gust. And it's a function of how hard you're maneuvering. If the wind's light and you're flying slowly, there's not a lot of acceleration. It doesn't seem to change very quickly. But if you start to fly more vigorously, it's leaning into the wind more, doing more maneuvers, then the estimate is faster. But hopefully that plot gives you a feel for how rapidly that estimate changes. Now, we can change the speed of the estimate. There's a tuning parameter in the EKF, which is the process noise that gets applied to the wind velocity states. And if you increase that process noise, the estimate will be faster to converge, but it will be noisier, or vice versa.
Yeah, so for people flying in really gusty conditions, we might be able to adjust some nerd numbers. Yeah,
that's right. Yes, it's the I don't remember the name of the parameter off the top of my head, but it's the wind process noise parameter on EKF3. So make it bigger so it's more responsive to gusts. Make it smaller to make it less responsive to gusts. Okay, so the next item that was added in that pull request, I'm just checking how we're going for time here, was the Barrow position error compensation. So I don't want to go into the details for this, but fundamentally, if you've got an autopilot with a port that allows the pressure internally to equalize with the outside air, or if you've got a fuselage with holes, the pressure inside that fuselage or inside that autopilot is determined by the pressure at the openings, and that's static pressure. And obviously, if you're flying where the opening is facing into the wind, it's almost working like a pitot tube, and it's increasing the pressure inside the fuselage. If the opening is to the side, it tends to reduce the pressure. And this is all a function of Bernoulli's theorem. You know, at the point where the opening is the airflow accelerated or decelerated relative to the free stream velocity? And if it's decelerated, it means that you're going to have a rise in pressure. And this is referred to as pressure altitude position error in aviation. And why is it called position error? Because it's a function of the position on the fuselage that you measure the pressure. And aircraft manufacturers take a lot of effort to put the static ports, that's the little hole in the fuselage that connects to the altimeter, to put that at a location where the pressure is as close as possible to static pressure. But there's always a little bit of error. Now, these parameters that have been added, whilst they're obviously going to be used for multi-rotors and hovering vehicles, they're also going to be quite useful for fixed wing. And for a fixed wing, you would only bother tuning the parameter for flight in the forward direction, because we've broken it down into forward, backwards, right, and left. Okay, here's an example from the little quad. And this is the great test aircraft, because it's got a cube orange sitting right on the top of the fuselage. It's exposed to free airflow. I haven't put any tape over the USB port. And that means when we fly backwards, there's a significant rise of pressure inside the autopilot. And you can see what I've graphed here is the barometric pressure measured in the two internal barrows minus the GPS altitude. And I'm looking for the change in that value with the airspeed. So I've now run the replay. I've got an estimate of airspeed, which is the difference between ground speed and wind speed. Plot that, and you can see how the measured height drops due to the increase in pressure. And that's an error, and it's quite significant. And when we're talking about 7 meters. Okay, now this is how you do the process manually. And once again, we can script this. The first step is to work out what your air density is on the day. Now, I have a few online calculators I go to. There are a number of them are available where you just enter in the temperature, the pressure, relative humidity. Humidity you can almost ignore. You can probably just assume dry air. I mean, it will get an acceptable result. And you get the air density. And then there's an equation that says that the static pressure, the actual pressure error, is the height times gravity times air density. So you could do the calculation, and that tells us that we had a static pressure error of plus 81 pascals. We then work out the dynamic pressure, which is half times density times airspeed squared. We get 108 pascals. The definition of position error coefficient is it's the static pressure error divided by the dynamic pressure. In other words, how much dynamic pressure, what fraction of the dynamic pressure is producing a static pressure error? And it's 75% here for a rear facing hole. It's very large. Look, a perfect pitot tube would be 1. So you'd hope when the forward facing opening on your pitot tube that all of your pressure gets recovered. The cube isn't the USB port on a cube is not a completely effective pitot probe. So it's 0.75. but it's still a significant change in pressure. So there we go. Now we've calculated the value for that, that parameter for flying backwards. Now we have a look at sideways flight. So if we're flying to the left, you can see when we're flying to the left, it means that the USB port is on the side of the autopilot where the pressure is reduced. And because the pressure is reduced, the attitude goes up. We do the same calculation. And then, by the way, there's a shortcut. You don't have to go through and calculate the pressure each way. I've done that for illustration purposes. You can use the shortcut formula, which is you set it to 2 times the height error times gravity divided by speed squared. So, and we get a value of minus 0.7. So in other words, there's a lot of suction on the side of the autopilot. So that's it in terms of setting these parameters for the Barrow compensation. So I think I can throw it open to general questions.
Well, I have a question. I guess you need to have already set up the wind speed estimation for this to work well, because I guess just using the vehicle's ground speed is not going to be accurate enough.
No, not well. Only if you're flying in still conditions.
Cool.
This is why I like replay, because I got the data I needed to do both calibrations in one step.
Right. Okay. Cool. Thanks.
Paul, it's Buzz again. So does that mean that the cube could be improved somewhat mechanically by drilling a hole in all 4 sides of it?
Yeah, but make sure you go all the way through. No, but actually there's a simpler solution, and that would what I do in practice is I just put a bit of tape over the opening. First of all, so that the USB card, little SD card doesn't fly out if I have a heavy landing, and that seems to actually largely eliminate the effect. But it's a nuisance. You've got to remove the tape and reapply it for each time you get logs off. But yes, if you do have holes around the corners, that reduces the effect. It doesn't go away completely, because you end up with, it probably gives you a more uniform drop by having holes all the way around the circumference. The drop tends to be in pressure. You still end up with a pressure drop inside from all directions, but it tends to be more consistent.
Got a question from Bill Geyer here. Bill, I guess you can ask directly if you like. All right, no mic. So Bill asks, how well do you think the wind speed estimation will work for helicopters?
Oh, okay. I mean, it would for a rigid rotor helicopter, I think it would work. For a teetering rotor where the rotor plane can tilt relative to the body, you'd have to have some estimate of what that tilt angle was. So, and that becomes tricky. For a rigid rotor, in theory, it would work.
So, Paul, we had a question on the live stream. Charlie Johnson's asking whether there would be a difference between in-turning or out-turning blades, presumably on a multicopter, whether you're like an X or an H style configuration of multi-rotor?
I haven't seen any evidence that it really makes a difference. Look, I know if you, I think when you've got coaxial rotors, I haven't looked at a log for an X8, for example, with the coaxial rotors to know what difference that would make. But yeah, direction of rotation doesn't really make a difference. I think what does make a difference is the shape of the booms. So, and also the size of the motors and the cells sitting underneath. Because anything you put underneath the rotor, like if you try to put a streamlined boom in to reduce windage drag during hover, then that the flow, the interaction with the flow and that boom results in additional flow straightening and additional momentum drag in that forward flight. So yeah, boom shape does make a difference to it.
All right, thanks, Paul. Right, so are there any more questions before we wrap up?
I have a question. After Paul, for putting all that effort into the estimation, sorry, the Barrow compensation, I'm wondering about, some of the GPS units, I think some of the hex ones have Barrow's barometers included. I'm just wondering if you would, consider trying to use one of those instead of, trying to work out those complex coefficients, etc.
Well, I've done that, but they also suffer from the effect.
Yeah.
Because they're shaped like a flying saucer, and the pressure inside equalizes through the little, the arming switch on the top, little button. Yeah. Tends to equalize through that, and that actually they have a drop in pressure. But it is uniform. The good thing about it is it tends to be reasonably uniform with flow direction.
Great, thanks a lot.
You might remember, probably it was going back 5 years, we had a couple of project members that tried to come up with a superior static port device for copters, having the concept of John Challenger, two circular plates, thin plates, very closely spaced, with the static pressure source to the middle of the plates.
Yeah, that was tests that I did, and it was stuck up above the aircraft.
Yeah, maybe how did it go?
It seemed to do. I've got to recall. It wasn't perfect, but it might have also been because the body was like it was about 10 centimeters above the body too. So
okay.
Yeah, and it was a bit of a blunt body over the top of the aircraft. So there might have been a sort of a pressure zone up there that I was getting a little bit, but like all of these things were significant improvements. I had two static ports on either side of this body. I had the double flat plate above the body, and it was an improvement, but it wasn't perfection, and I'm like, I was trying to get sort of less than a meter of variation when I was doing 15 meters a second and stuff. So I can't remember my threshold for what was good and what was bad, but I think most people would be really happy if their Barrow only moved by a meter or so at 15 meters a second. So
yeah, I'm on this aircraft. I was seeing 7 at 13 meters per second.
yeah, I've seen crazy numbers of 50 in some aircraft in the right circumstances. Yeah. So yeah, it's amazing how bad it can get.
Yeah, I think the takeaway for me from going through this exercise is that if you take reasonable precautions in hardware and then you back that up to try and get the variation, that positional error effect, less variation with flight direction, so it becomes more uniform, then this algorithm will do a better job. So it's really a combination of the two.
Always try and fix it in hardware before you look at
Absolutely.
the solution.
Oh, I'm not sure you said, sorry if I can just jump in one more time. So how low do you think you got the interference in the end? Do you think you got it, like, it looks like, you know, you had 8 meters or so of error beforehand. Do you think you got that down to maybe like 1 meter or something, like Leonard was suggesting, was a good level of acceptability?
Got it down to about 1 meter with a bit of tweaking. So it certainly was a noticeable improvement. So it was in the order of 1 meter. I haven't gone back and actually really analysed that follow-up flight log to see how much it was. But visually, it no longer became a point where I became concerned about the height drop and started to bail out.
Yeah, no kidding. Awesome, thanks.
All right, well, there's no more questions. Just like to everyone to give a huge thank you to Paul. So thank you very much. It was absolutely brilliant. It's what a talk to start the conference off on. Really fantastic new feature and fantastic description. Thank you very much, Paul.
Yeah, and I would just like to thank the audience for sitting through an hour of physics and EKF.
Yes, you're getting a lot of thanks there on the chat, and so really enjoyed that. It's brilliant. So now, should we take a break for a minute or so before we move on to the next talk, or should we jump straight in? What do you think? Anyone need a toilet break? Well, no one says anything. I think we're going to leap straight into the next talk. So the next talk happens to be me. But in this case, it's me wearing a different hat. So I've actually logged into Zoom twice, once as the conference organizer here, and then once as myself for giving my talk on my Linux box. So I will just transfer over to my Linux box, just a second.
You can just give me another second too to restart the recording, that'd be great.
Sure, that's fine. I'll do the same. All right. Now I've got to stop some local echo by turning off my audio here. Great. Okay. So is that coming through okay?
Quick question, Tridge.
Mm-hmm.
So this is the time slot you'd swapped with Tom for?
That's right. Yes, because Tom didn't have his slides ready, so he asked if he could swap. And so we're running a little bit ahead of schedule, which is great, because some of the talks might go a bit long, and so it gives us plenty of time for questions. So Tom is going to be tomorrow morning.
Yeah, tomorrow morning, exactly. Thank you.
That's right. Tom will be tomorrow morning, and I'm giving my systems update starting up in just a minute. All right. All ready, Randy? All the recording and things?
Yep, I think I'm already recording. Yep.
All right. And if anyone wants to follow along my slides, there's a link to my slides in the schedule. And so you can click on that and follow along and look ahead and work out which of the boring bits you're going to go away and have toilet breaks and coffee in. So I'm going to share my screen and then start the presentation. Now, just confirm that everyone can see that okay?
Yep, looking
Confirmed.
good.
Yep.
Okay, great. All right. Well, thank you all for joining in. So this is a systems update. This is something I've done for the last few years, give a sort of update of the overview of what's happening in the project as far as low-level drivers, the RTOS, the HALs, that sort of layer. And so that's what I generally call the systems level of ArduPilot, as opposed to the sort of higher level flight control and state estimation and other areas. So to kick it off, I thought I'd give a bit of a summary of how things have been going over the last year. it's been a very big year in terms of development. There's been a lot going on. We've had a total of over 5,000 patches have gone into ArduPilot, representing over 3,000 PRs going through in the last year, which is really quite incredible if you think about it. That's an awful lot of code, an awful lot of code review, a lot of development, and a total of 173 people have contributed to just the main ArduPilot repository. That doesn't include all the contributions to the documentation and MAVLink, MAVLink, you know, all mission planner, and many, many other repositories that make up the overall ArduPilot ecosystem. Also, just in terms of code change, the total number of lines of code that have changed in some way in the last year is 280,000 lines of code. And that's just in the main ArduPilot repository, only counting the C++ and header files. And we've only got 500,000 lines in the repository. So that means that more than half of the lines of code in ArduPilot have had a change in some form in the last year. Probably about half of those is spelling fixes from Pete Hall's patches, I would guess. Sorry, Pete. So a very, very large amount of code changes in the last year. And so it's been huge contributions by the team, and really greatly appreciate everyone pitching in. Firmware size has become a bit of an issue over the last year, and I've put there the firmware size for the FMUv3 firmware over the last 4 years at about the time of the developer conference. And you can see back in 2018, it was about 940 odd K, 938. Leapt up with a huge number of features. We had a very big year, 2018, 2019. We leapt up to 1.3 megabytes. So also we changed the default optimization to be 02, I believe, which increased that on the 2 meg boards. A bit smaller for 2020, and then another huge leap in the last year, another 200K. So we are actually, if you extrapolate out a little bit, we're going to start running low on space on the 2 meg boards fairly soon, particularly on the F7 2 meg boards, which use flash for storage, because and the H7 as well. So for example, an H7 2 meg board uses 3 sectors, 1 for the bootloader, 1 and 2 for the flash storage, which means, you know, 3 times 128, that's a lot of flash being used taken out of your 2 meg that you can't use for code and data. And so we've got to start thinking very seriously about flash space. It's even more critical on the 1 meg boards. And so just on the right here, I've put a little table as of this morning, the 4 boards that have the least flash space free. And these numbers here are in bytes. So that's the number of free bytes we have on those 4 boards. And this is one, the Omnibus F4 Pro is one that Henry Wurzburg flies a lot. And he noticed, for example, that some current pull requests, if he applies them to master, then his favorite board, the Omnibus F4 Pro, doesn't build anymore. This is with plain. The copter build still has a bit free, about 20K free on those, but the plain build is very, very close. So what that basically means is that we are getting a bit of a critical issue with some boards as far as flash space. And so we've been talking for a while now about a custom firmware server, where we have a custom.ardupilot.org that operates somewhat like our terrain firmware server, terrain download server, terrain.ardupilot.org. If you've never seen that, then pop in terrain.ardupilot.org into your favorite web browser, and you'll find it's a very useful tool. We're hoping that we'll be able to get a custom firmware server as part of a GSOC project over the coming months. And we've got a promising candidate student who's applied for that. So I'm hoping that that will be successful. And with the custom firmware server, it'll allow users, for example, on the Omnibus F4 Pro, they could turn off a whole bunch of features to be able to, you know, turn on just the features they need. In order to do that, it does mean we're going to have a lot of restructuring of the code over the coming months to take full advantage of that capability. For example, I would like to make the quad plane capability in ArduPlane optional. which will cut out all of the VTOL support, all of the copter support, AP motors, etc. And that would be probably 150 or 200K maybe worth of firmware space, around that order, maybe 100K. I haven't actually measured it because I haven't got that optional yet. And that would make it possible to, if you're flying on a pure fixed wing platform, you don't have VTOL, you'd be able to deselect that and save a lot of flash space and get a custom build. But I suspect by this time next year that a fairly significant part of our community is going to be flying custom firmware builds with just the features that they want. And so it's going to become more and more important as we get these new features, because a lot of our recent features have been very flash heavy. I forgot to say at the beginning that I'm very happy for people to ask questions during the talk. So feel free to just unmute yourself and pop up a question if you'd like to. And I don't have the chat open, so I won't notice it in the chat. So, but if you don't have a microphone, then pop it in the chat and somebody else can relay the question if they've got a microphone. All right, so that's basically what's been happening as far as development summary. So very rapid development, but there's a consequence of that rapid development that we are consuming our remaining flash space fairly rapidly. We do have a bit up our sleeves on the 2 meg boards because they're currently built with optimization 02. Most of them are. We can switch that across to space optimization if need be with a little bit of a performance penalty, and that would save us a bit of flash space. So we do have a few options to delay the problem of running out of flash in the 2 meg boards. We don't have as much luxury on the 1 meg boards because we're already doing that on our 1 meg boards. All right, next major thing that's happened just recently is the shift to ShibiOS 20.3. We were on a 2018 version of ShibiOS, and we'd been on that for quite some time. And we recently updated it to the 20.3 version. It was really quite an uneventful change. And I'd like to say, greatly appreciate the assistance from Andy Piper and Sid in that shift to the 20.3 ShibiOS. They both contributed a lot, especially Andy in that work. It was actually mostly fairly minor bug fixes, made it quite an easy update. It was easier than the previous RTOS update. There was a few little tweaks we needed to make. But that got us a new release. The reason for the update, the motivation was twofold. One was supporting some new microcontrollers, in particular the new G4 STM32 G4 microcontrollers. And the interest on that was the G4 is a low-cost small microcontroller that supports FD-CAN. And over the coming months, I think that there's going to be quite a bit of emphasis on supporting higher speed CAN bus. And this is mostly because high speed CAN bus just gives us more bandwidth. And we are already finding that if you have a lot of CAN peripherals enabled, for example, CAN ESCs and CAN servos, if you enable a lot of those at the same time, as well as GPSs and other devices, rangefinders, etc., we're pushing the limits of the 1 megabit CAN. In practice with 1 megabit CAN, you get about half a megabit of practical bandwidth available with all the overheads of UAV CAN and the framing, etc. And we're basically, utilizing most of that on a machine that's set up, for example, a quad plane that's set up to use for all of its VTOL motors to be CAN ESCs and with some extra CAN servos, etc. It's running quite close. So I think we're going to be pushing things on FD-CAN, and so having a microcontroller for a low-cost AP peripheral based on the G4 microcontroller is going to be really good. And there's already 2 companies that I'm aware of that are developing AP based peripherals based around the G4 microcontroller based on this work. It also adds support for QSPI, yeah. And so
Tridgell, I have a question. There?
Yep.
Yeah, does that mean we're going to move to the UAV CAN 1.0 spec?
So I addressed that a little bit later in my talk, but the basic answer is that we'll probably support UAV CAN V1, but Sid and I are also considering the possibility of supporting a variant of V0 that can handle higher data rates. And that's quite attractive for various reasons, but I'll discuss that in a bit more detail later in the talk.
Okay.
So also adds QSPI support. So QSPI support allows us to have external flash. So flash that's not incorporated directly into the microcontroller, and instead have the code and data on an external flash chip. And that's something that Andy Piper's been working towards on a racing board out of the UK that supports that. But I think more and more flight controllers are going to move to having a few megabytes of QSPI flash. And Andy's got a draft pull request up for that on this one board. And it's going to be quite interesting because it means that we'll be able to start expanding flash size without having to move to a new generation of microcontrollers with 2 mega flash, because basically ST doesn't really have microcontrollers in the class that we use that have more than 2 mega flash. So having the ability for some new flight controllers in the future to augment their flash space with a QSPI flash part is going to be very valuable to be able to cram all the features we want into the flight controllers. So really interesting work being done by Andy, and I'm be very interested to see when that's fully working. And so that was a strong motivation to move to 20.3 to get the QSPI support. That is also going to require a bit of restructuring inside ArduPilot, because to gain the most benefit from having the QSPI flash support is going to require that we start marking up functions as being time critical, and that those functions should be, the code for those functions should be in RAM instead of flash, which reduces the worst case latency. The microcontroller will of course cache the code using its onboard cache. It's got a set associative cache it'll use for the code, but the worst case latency would be quite high if it has a cache fault and has to pull the cache out from across the QSPI. So particularly important for interrupt handlers. So we will definitely need to mark all of our interrupt handlers as being in RAM functions, but there'll be quite a few other time critical functions as well that we'll need to mark. And so we'll basically be giving up some of the RAM on these boards. Luckily, they've got quite a lot of RAM, and dedicating that RAM to being in RAM copies of the time critical functions. And so that'll just be a little markup on functions. So a little attribute that we put at the end of a function name to mark it, to place it into a section of the a flash segment in the ELF binary that gets copied to RAM at startup to make sure that it runs very, very fast. Any questions at all about the Shibios 20.3 shift before we move on?
Yeah, just on the quad SDI, obviously that's quite a motivation from us to push on that as well.
Yeah, definitely.
Towards that, hence Sid working on that.
Fantastic.
Yeah, look, one of the things that you're just talking about, the time penalty, I'm very keen to see when we actually get there, because ST put a lot of effort into claiming there is no time penalty. So it'll be very interesting when we actually have the hardware to actually do some of those comparisons on those critical.
Yeah, the cache control is going to be quite critical. Unfortunately, we've got fairly large data usage in ArduPilot. You know, for example, the EKF uses 15, 20K per core, and it accesses that in from the point of view of the microcontroller an essentially random pattern. And we definitely need that cached. So I suspect that the cache algorithms are going to be struggling a bit with the prefetch from QSPI. I also suspect that the prediction, etc., that they've got in there is going to struggle, but it will be very interesting to start measuring it and seeing exactly how well it performs. But what we'll need to do is do some careful profiling. It may be worth actually getting some of the developer tools set up. There are ways of setting up STM32 so they can sort of stream real-time information, much more detailed information than you can get over ST-Link, out to an analyzer that can analyze the behavior of the microcontroller. And it might be worthwhile if Sid or one of our developers had access to those sort of tooling to be able to do some analysis of the performance and start adjusting, because profiling this stuff is quite challenging. But we just need to get it working first, and then we can do some course level profiling using our existing tools, and then start working out, what are the key functions we have to shift into RAM. We may even need to make it dynamic, where it actually depends on the configuration. So if people enable particular features, then we shift certain functions into RAM. Obviously, if they've enabled EK3 versus EK2, if they don't have EK2 running, you wouldn't want to have a whole lot of the EK2 code in RAM. You'd have that, just leave that in flash, leave it dormant. We might be able to just let the cache handle it, or we might need to do things in a more custom fashion. But that'll be something we'll find out in the coming months. And so at the moment, I'm just cheering on Andy and Sid from the sidelines as they do this very valuable work. But I have ordered one of those boards, that SP Racing board that's capable of doing this. Unfortunately, the post at the moment with the pandemic is not great, and it hasn't arrived yet.
Yeah,
any other questions on that?
Oh, the only other concern I've got with it, obviously, is as we start, moving things into RAM to make it easier to add more flash. Yes, we have now 4 times the RAM that we used to have.
Yep.
But I'd hate to see people getting too RAM happy, or any additional flash we had will soon be null and void by, overuse of RAM. So please, everyone, be careful. Hardware's fun, but it has long cycles, and don't get too trigger happy on the RAM.
Yeah, that's right. That's right. We have we're at the moment the biggest RAM user actually on H7 boards. Even the default configuration is our buffering for the logging. We default that on H7 at the moment to 200K, just because we've got a lot of free memory, and so we might as well use it for buffering. And it means, you basically never lose a block to your SD card, even if you've got the cheapest, worst SD card around. But we can obviously pare that back and start using more of that for code once we start bringing in the QSPI work. All right, so moving on. So the next really big architectural change that I thought worth mentioning from the last year was the addition of the DAL, which is the Data Access Layer Abstraction. And this was basically the key enabling feature to allow us to do the new replay, high fidelity replay system. And Paul showed to very good effect in his talk earlier this morning, just how effective the replay is for doing analysis, being able to attune the EKF, and also analyze any issues that you have with the Kalman filter. The DAL is an isolation layer between EK2, EK3, and the rest of ArduPilot. It means that the EKFs are only allowed to access sensor data, system state, etc., and timing information via the DAL. So it acts as like a choke point in the autopilot, where the EKF is required to funnel all of its requests via the DAL. And the initial design of the DAL was put together by Peter Barker, and it did a fantastic job in getting the abstraction right. So thank you very much, Peter, for your work on the DAL and on the new replay. So by doing this, it means that we can log all of the interactions between the EKFs and the rest of the system, and log it very precisely. It means that the data structures that we log are in fact identical to the data structures that are used by the EKFs to access the rest of the sensor data, all of our IMU data, Barrow data, timing data, etc. So it means effectively the EKF is reading from the log stream because it's actually the same log structure that is used when you have the accessor functions. And we guarantee this property by, we actually have continuous integration tasks. So every time you do a pull request, there's a CI task that links the EKFs to just the DAL and not to the rest of the system. And if it doesn't link, then that means that somebody's been naughty and they have gone and put in a function into the EKF that accesses a piece of data not going via these log data structures. And that would be a violation that would then potentially break the integrity of the replay system. For those who are unfamiliar, the replay system is our way of rerunning the Kalman filter after a flight based on a log data. And it means we can change the code if we get an issue with the EKF, a state estimation error of some sort, and we want to try and apply a bug fix. We can actually develop the bug fix and then run that bug fix against the exact flight data from the flight in question where the problem showed up, and then compare the new behavior of the EKF versus the old behavior. It's an incredibly valuable tool, and we've had it for a number of years, but it basically it bit rotted for a while. And there was a couple of years there where the replay tool, its fidelity was poor enough that it wasn't really usable for its intended task. And with this new dial system, it's now gives extremely high fidelity, and it's now very, very useful again. And so by locking it in this way through a CI, locking it in through this dial abstraction, it's guaranteed that replay will remain as a useful tool into the future. We also, in the CI, we actually, we do a SITL flight test in CI, and then we run the flight test through replay, and we do a bitwise comparison of the resulting state estimation. And we check that, to the bit, every single floating point number that is generated and integer that is generated by the EKFs is identical to the one in the original flight when we run it through replay, which is the basic hallmark of a good replay system. So that has locked things in. And so if you're wondering why there's, when you're trawling through the EKF code, you see lots of references to this dial function, that's why. And now we're not planning for the dial to be used in the rest of the system, because that would in some ways defeat the purpose of the isolation for replay. So dial is an EKF only abstraction, but we have deliberately made the APIs for the dial extremely similar to the APIs for accessing the rest of the sensor layers, which means that you should find it quite familiar. You basically replace, for example, compass get field with dial get field, and or dial compass get field. And that gives you the same API, but via the dial. So thank you again to Peter for his work on that, and that's going to be incredibly valuable going forward. So the next area that I wanted to focus on in this talk is what's been happening in AP File System. So AP File System is our abstraction layer for the file system. And it provides abstraction for the POSIX file system. So for example, the SD card, it allows you to access files on your SD card, but it's much, much more than that. And in last year's talk, for example, I introduced the param file system, which allows us to download parameters via the MAVLink FTP protocol. And essentially, that gave us a speed up of, much more than an order of magnitude in parameter download. And we've already had quite a few comments from users who are trying out the 4.1 branch, the latest builds of ArduPilot, that when they connect, they get much, much faster parameter download. And that's basically because Mission Planner, thanks to Michael Oborn's great work, has been extended to automatically use the FTP download of parameters when available. The same with MavProxy. So what I was going to talk about this year was we've expanded the AP file system a lot in the last year, and many developers and users may not be aware of the additional functionality. It's also that each time I give one of these system talks, I like to introduce a new feature. So over the last few days, I've developed a bunch of new features which I think might be of interest to a number of our users. And so I was just going to do a bit of a demo of these. So the key new features is I'm adding a @mission file system, which allows us to upload and download missions extremely quickly using MAVLink FTP. And it also gives us atomic mission upload. So when you upload 1,000 waypoints with the mission FTP MAVLink protocol, it's around 10 times faster, but it also means it applies those waypoints as a single unit once all the waypoints arrive on the vehicle, and rather than applying them piecemeal during the upload, which means that you don't end up with an inconsistent mission. So if you want to change a mission while the vehicle's flying, you can do so using a low bandwidth link much more effectively, but also not end up with half a mission at the other end. It will either apply the whole new mission or none of it, which is a really important property for, you know, if you're doing large missions, particularly on a vehicle that is at the end of a slow telemetry link. It also handles fence and rally upload and download. So you can upload and download your fence points and your rally points. And just as a bit of extra, I've also added parameter upload using FTP. And that's much, much faster than uploading parameters using the existing protocols, roughly 10 times faster in my testing. That also has the nice property that it applies all the parameters in one go once they get onto the vehicle, which again ensures that you end up with consistent parameters. And it also gets over the property of the double download. People often, when they're, say, setting up a new vehicle and loading 1,000 parameters from another vehicle, and you have to load once and then you re-download the parameters to fetch them again because you've had a bunch of enable parameters. For example, QEnable, which enables the quad plane capabilities, or you're enabling a second battery monitor, and you then have to refetch the parameters, then re-upload again. And that's the dance that people are doing a lot at the moment. And they have to refresh and then re-upload again, and then acknowledge all the little OKs, etc., in the user interface. So that's fixed using this MAVLink parameter upload, and it uploads them all in one go, and it automatically handles the retries and the looping necessary within the flight controller so that it handles all the enable parameters correctly. So I'll just switch across to give a demonstration. So what I've got here, I've got a cube orange sitting here on my desk, and so there you go. I might as well give the full feeling. So there's my desk with there's a cube orange sitting in the middle of it, along with a whole bunch of other electronics. And this, of course, works with any of our flight controllers. And then over here, I've got a 3DR. An ancient 3DR radio, SIK radio, and so that radio is, you know, out of my drawer from a long, long time ago that I've got connecting up to the vehicle. And so on the, I'll just share my screen again so you can see that again. All right, so so I'm connected into this vehicle here, and I'll just show you a few little features that we've now got. So first of all, you've probably already seen, so the parameter FTP, I can do that, and I can receive all of the parameters in the vehicle very, very fast. That's fetching the parameters. I've got both a USB link and this ancient slow SIK radio. If I set link 1, then I'll be using the SIK radio, and you can see here the parameter download that I'm doing here. You can see the little progress showing there and on downloading. So that was over that slow SIK radio downloaded the parameters in just a few seconds. And on the USB, it's basically instantaneous. So the new features is that what I'm going to do is I'm going to, I've got my map here, and I'm going to clear the mission. And then I'm going to do a waypoint FTP load this mission that I've created. And so I'm going to do that. I'll do it on the USB one first to show you how fast it is over a USB link. Then I'll do it on the radio link. And what it's going to do is it's still loading that mission. It's loaded it all already. It only takes a fraction of a second over USB. And we can see we have a mission here. And this is taking advantage of the expanded mission space we've got in the in boards F7 and H7 boards. So we've now got up to about 1,300 waypoints we can have now. And so this is a 1104 waypoint mission created using the very cool little skywriting text mission from Mission Planner. Thank you very much for Michael Oborn for showing me how to do that. So we have ArduPilot DevConf 2021 as a mission, and we can load that very quickly. So what I'll do now is I'll just switch back to the slow SIK radio link, and I'm going to download that mission. So WP FTP, and to download that mission from the flight controller across the SIK radio. And you can see the little progress up here. So it's got about 200 now and coming up on 300. So it's making good progress, 400. And so this is the sort of link speed you might get with a slow SIK radio, you know, or like an RFD 900 running out to an aircraft in the field. And nearly there. There you go. We've now loaded 1,104 waypoints, and it takes around 20 seconds or so, a little bit less on these radios, which I'm quite pleased with. If I ran it with the old protocol, then we'd be waiting several minutes. It's about between a 10 and 20 times speed up over the old protocol. So it makes it much, much more practical. But more importantly is for many people is the fact that it's atomic. It means that when you end up with the whole mission as one lump. So you don't, if your aircraft is actually flying and you want to replace the mission with a new one, you can do so. It also does partial mission upload. Thanks to Tom for suggesting adding that to the protocol. So you could replace, for example, just the middle section using FTP, or just the end section, or just the beginning. There's flags in there for whether it should clear the mission when uploading. And that makes it really nice for doing partial uploads or shifts in pieces of the mission. So once this gets into our tooling, into the ground station, I think this is going to make dealing with large numbers of waypoints a lot nicer. I was also going to show you a parameter load. Actually, I might do that at the end. I'll wipe the parameters on the vehicle and load them from scratch as a demonstration at the end. But first of all, I want to show you what's been happening in the Sys file system. So there's been a lot of extensions happening in the Sys file system over the past 6 months or so, and work that's being done by Sid and Andy and myself in particular. And so there's a lot more files in here than there were last year. So we have, for example, you can look at a lot of system details. For example, if I go and get the sys memory.txt, and I'll just get it to minus in mav proxy means fetch it to standard output, which means it just displays it on the screen, right? So what that is doing, I'll just switch to the USB for faster. What that's showing is all the different memory regions. And there's actually 6 different memory regions, different types of RAM on the STM32H7 microcontroller on this particular board. And what it's showing us is the size of each memory region and how much of each memory region we're using. And we can see, for example, that we're using only about 10K or about 8K of our DMA-able memory. This type here tells us what type of memory it is. This particular one, if you know how to decode it, this means that this is the DMA-capable SRAM4 memory. And this one is the one that's used for the SDMMC for the SD card. So you need to be a bit of a system developer to know how to decode these memory types. But it can be very useful when you're a developer looking at the performance and where your memory is going. So we can also download, so if I get something like DMA.txt, then this shows us the DMA contention. I'll just pop that up the top of the screen there. Might be easier to see. And I might raise my font size a little bit. So that should be a little bit easier to read for people particularly on the live stream. So this is showing us, how many DMA operations we've had on each DMA channel. And it's also showing us how much contention. Now, on this particular board, we're not, with this particular set of peripherals, we're not getting any contention at all. This is all 0% contention. If I had a different set of peripherals on here, I would start seeing DMA contention in this column. And very, very useful for analyzing performance issues. So if you do get problems with particularly UART to I2C and SPI contention causing performance bottlenecks, you can work out exactly what's going on here. And then we've got parameters that allow you to do things like disable DMA on a UART transmit or receive, for example, to prevent contention with another device like an IMU or an I2C compass or whatever. And so this type of analysis is incredibly useful when you're trying to do performance analysis on your board. Some other things in Sys, we can have a look at some CAN stats. So if I go and get the what's been happening on the CAN bus. So I've only got one CAN peripheral attached to this board. This second GPS is the nice high-tech Mosaic, their nice new Pro GPS. And so we should be able to see a few stats on that. And we can see exactly how many transmit requests. And we can see that we've lost one CAN packet. So we've had 1,580 transmit requests, of which one of them has been lost. And we've had, 1.5 million received packets since this booted. And you can see whether there's been any aborts or overflows or bus off errors, etc., which is really useful for seeing the quality and performance of your CAN bus. So if you're doing a lot of CAN work, you've got a lot of CAN peripherals, it's worth knowing how to look at the stats on each of your CAN buses and know what's happening with that. So you can also do a lot of analysis of things like the threads, how much memory you've got for each thread and the amount of stack space available. So this shows you all of the different threads. And as I'll describe later in the talk, we've now switched to a UART, a separate thread per UART model. And so you now actually have a separate thread for each of these UARTs, and you can see the amount of stack space being used. This is the free space and total space in this last column. And so we can see on the interrupt stack, we've got 1160 bytes, 3 out of 1500. So we've got plenty of spare room there. And you can see you want to check whether any of these are getting low. If this first column is getting very low, then it might be an indication that you're running things a bit close on stack space. And you can see the priority of each thread and where the memory is located. Another good one is the tasks. So that allows you to get some information on all the different tasks happening inside IGPilot. You will find that when you first fetch the tasks, it'll give a failure. That's because we don't allocate the performance monitoring to generate this table until you fetch the task for the first time. So you have to fetch the task, then wait a few seconds, and then it starts populating that task set. And then after that, you can then fetch it. So I'd already fetched it earlier before I started the talk, which is why it gave it straight away. And we can see exactly what the performance is, the total CPU costs, and the minimum maximum time in microseconds that each of these tasks is using. And so you can sort of nail things down a little bit as far as the performance costs, with brought down to some quite low level. You can sort of see, the various update functions, logging functions, etc. And it'd be good, actually, I should probably work with Henry a bit more to put in some examples in the wiki and showing exactly what these numbers mean for when you want to do some performance analysis to see, where your CPU is going. What else have we got here? We've got the UARTs. So you can bring up detailed information about your UARTs. And this shows you each of the UARTs you've got on the system. And you've got a little star here for the ones that are using DMA. And it shows you the sort of transmit and receive events. The receive number of blocks and that sort of thing. So it's again one that we should put up more information on decoding this in the wiki. And then this persistent PAM, that's for when you've got temperature calibration on your IMUs and it stores the persistent data inside Flash. It allows you to have a look at what that persistent data is. In fact, in the factory, you can now embed a persistent set of parameters that will persist. They're persistent in the sense that even if you wipe your entire Flash by changing firmware, like from copter to plane to rover to blimp, it will still persist those parameters. So these are common parameters that are persisted even across a firmware type change. And that means that they can be placed into the firmware in the factory. Typically, you would put the temperature calibration data for factory temperature calibration in these persistent parameters, which means that when you ship the flight controller, that data is built into the flight controller across any future firmware, and it means that everyone will benefit from the factory temperature calibration. And I'm looking forward to that start being rolled out from the various ArduPilot vendors in the coming months, that capability, and start seeing some factory temperature calibration going on. All right, so that's probably enough information about the Sys file system. And I was just going to show you the parameter upload. So what I'm going to do is I'm going to set the format version on this board to 0, which wipes my parameters when I next reboot. And so what I'm going to do now is reboot the flight controller, and that'll come back up again, this time with completely blank parameters. So it's now come up as just a default plane for this particular board, and you can see it's gone into failsafe because the default is throttle failsafe, and I don't have my transmitter turned on. And then I'm going to show you, so if I do param FTP to fetch down the current parameters, I'm going to set the link to the little SIK radio, that radio. All right, we're now connected over that SIK radio, and I'm going to do a param FTP load of my parameters. So this will now load all of the parameters of the vehicle via the parameter FTP protocol. So that's now uploading. You see the percentage going up there, and done. So it's loaded all of those parameters in just a couple of seconds, even across an SIK radio. So it's a very efficient way of downloading. If I now download all the parameters, it takes a little bit longer via the SIK link, but still very, very fast. It's half done. And there you go, all done. So if I now compare those parameters, you can see that the only differences are those ones you expect to be different, because we deliberately omit certain parameters like the airspeed, offset, mission total, number of resets and things from our parameter uploads. So that means that's demonstrated the way of restoring all the parameters onto a vehicle, including all of your enable parameters, and storing it very, very fast over a low-speed radio link. All right, any questions on that before I go back onto the rest of the slides? All right, so I'll move on. So what to have done that one and move on to the DMA changes. So there's been a lot of changes in the way we handle DMA in the last year. And a lot of this work was done by Andy Piper, and I really appreciate how Andy's dived into the lowest level of the HAL for ArduPilot, the Shibios HAL. It's done a fantastic job. So we used to use what's called binary semaphores for shared DMA. So ArduPilot has a slightly unusual feature in projects of this type, in that we allow for sharing of DMA streams between peripherals. So you could have a UART and an SPI bus both sharing the same DMA stream. And the reason we need that is because we have in ArduPilot a very, very rich set of sensors that a lot of people put on their vehicles. And they have more buses and more peripheral types than they have available DMA channels. Combined with the fact that there's each type of microcontroller that we support has different restrictions on which DMA streams can be used by which peripheral type. So, you know, for example, SPI1 might be on an F7 board, be able to be used by only 2 different DMA streams, you know, specifically numbered DMA streams. And I2C3 might be able to be used by a different 2 where there might be 1 in common. So there's this little matrix with overlap of DMA streams that are able to be used. And some time ago, when we did the HAL Shibios work, we introduced an automatic DMA resolver, originally written by Sid and then modified subsequently by both Andy and myself, that it tries to automatically allocate DMA streams to peripherals. And it can't do a perfect job because it doesn't know at runtime what peripherals a user actually cares about. So we can't really know whether the user is going to be using UART2 or not, or whether it's important. But we do our best, you know, to guess at the likely usage and allocate those DMA channels. But we allow this sharing, and by allowing sharing, we can use DMA for a lot more peripherals. And that means more CPU available for Paul to use in the EKF, and for Leonard to use in his filters and flight control. And occasional others in the dev team get a look in and get a few % of the CPU if they're lucky, for things like avoidance and that sort of thing. So now binary semaphores had the disadvantage that they can't do what's called priority inheritance, which means if a low priority thread is holding a binary semaphore on a DMA channel, and my apologies for those of you who are not familiar with these sort of concepts, hopefully it'll become somewhat clear as I explain. So when a low priority thread is holding that binary semaphore, and a high priority thread comes along and wants that semaphore, it has to sit and wait until the semaphore is available. But that low priority thread may not actually be scheduled very quickly, which means that the high priority thread could be waiting for a much longer time than it really should. So what we want to use is what's called priority inheritance. And priority inheritance is a system in an RTOS where the lower priority thread that is holding up a high priority thread gets its priority automatically boosted to the priority of the highest priority thread that is waiting on the resource that it holds. All right, so basically that guarantees that it completes as fast as it should, according to the thread priorities we have. It means that our main thread doesn't sit around waiting for a low priority thread that is holding a mutex. Now, we have priority inheritance on mutexes in Shibios, but we can't do them on binary semaphores due to the way they're structured. And so we had to switch across to using mutexes, which required quite a bit of restructuring of the code, largely because mutexes have to be associated with a thread in order to do priority inheritance, whereas we were using binary semaphores in interrupt contexts in a number of places, particularly in things like DShot. And so thank you very much to Andy for doing that restructuring. And we are now switched across to using mutexes for our shared DMA, which is the first step along the way of the complete DMA restructuring, which is planned for ArduPilot. So the next stepping stone that I want to do in the coming months is to move us to dynamic shared DMA assignment. At the moment, as I mentioned earlier, we assign our DMA streams to peripherals at compile time, and we don't do an optimal job of it. In some cases, we do a very bad job of it. In some cases, we do a better job, but we basically can't do the perfect job because we don't know which peripherals are actually going to be used in practice. We do for things like IMUs. We know that the primary IMU is going to be used, but we particularly don't know it for things like the UARTs and for timers associated with things like DShot. And for the DMA streams that are associated with those peripherals, we can't make the decision accurately at compile time. So we'd like to use to a runtime optimization of our DMA stream assignment. And that restructuring really needed the new work with the mutex first to be done first to give us the new structure. And then I'm planning to start bringing that in after 4.1 is branched and start bringing in dynamic. And that should make for much better performance in some cases. At the moment, you need to go in by hand in some cases and disable DMA on particular UARTs to get the best performance. You shouldn't need to do that in the future. That should be completely automatic with the dynamic assignment of DMA channels to our peripherals. So look for that in an upcoming PR, and you'll be getting more performance out of your boards in future. We're also going to be moving to peripheral aware DMA allocation. You may remember when I was doing that little demonstration before, where we've got here the the memory. So if I have a look at the different memory regions on this board, and you can see that there's these 6 different memory regions on the H7. And there's actually a complex matrix as to what peripherals are allowed to do DMA with what memory regions. And at the moment, what we're doing is we're cheating by using the SRAM4 memory region, which is equivalent to like O-type blood as far as donations. So the SRAM4 can be used for DMA for any peripheral except the SD card, but it's not optimal for just about anything. In fact, it's slow because to get to SRAM4 requires that the little memory requests get routed all across this complex bus, and which means our DMAs aren't nearly as fast as they should be. And so what we're planning to do is move across to a peripheral aware memory allocation scheme where we, when you allocate a piece of memory for a peripheral, you'll have to say what peripheral you want it for, and then it will automatically allocate the optimal memory for that peripheral based on what peripheral type it is. And that should make a huge difference. Well, we don't know how much of a difference it's going to make. We're hoping it will make a noticeable difference to our DMA performance, particularly for things like bidirectional D-shot, which is very sensitive to timing of DMA operations. But we'll actually need to do some performance analysis to see how much of a difference it makes for other types of operations. But for latency sensitive operations like bidirectional D-shot, we're expecting that it will make a significant difference. All right, any questions about DMA changes before I move on? Or have I sent you all to sleep? Nope, okay, moving on. So UART handling. So ArduPilot, back since 2016, we shifted to what we call the thread per bus approach to RTOS handling, where basically we have a separate RTOS real-time operating system thread for every bus in the system. And we did this for all I2C buses, all SPI buses, the ADC, and you know, the analog in, I mean, and some of the other buses like SD card and things, but we didn't do it for the UARTs. And the reason we didn't do it is we were concerned about the amount of memory being used by the stacks for all of those UARTs, because quite a few boards have a lot of UARTs. So I think the one with the record, I think it might be 8, is the Maytech. I've got it on my desk here somewhere. There it is, Maytech H743. And so we've got an enormous number of UARTs on that board, which is great, really good for users to be able to have so many UARTs. But with a thread per UART, that's an awful lot of stack space. And so back in 2016, we made the decision that we would have a single thread for handling UARTs, and we would operate on each of them asynchronously. And so Andy Piper identified that was a significant bottleneck, and in the performance analysis work that he was doing. And I completely agreed with him. And so we ended up switching just in the last few months to a thread per UART model. And what we found was that the reduced latency in dealing with UART requests meant that we were able to reduce the buffer sizes on the UARTs considerably. And it meant that even though we're now paying for a lot of stack space in our UARTs, so an extra 600 or 700 bytes of stack per UART, we save more than that in terms of the reduced buffer space we need per UART. So this change actually meant that we got our cake and can eat it too. We gained performance in our UARTs, and we reduced the total memory footprint of ArduPilot, which was really nice to see. It was a very big win. And so this means that our UART responsiveness is now much higher. It means that with a dedicated thread that's sitting there waiting for data on that UART and waiting to pump more data out as the UART has space available, we're able to get considerably better throughput on all of our UARTs. And this is most starkly seen with, we changed the way we do the buffering on USB, and we ended up with about 3 times the log download performance on H7 boards for log download over USB. But it's also considerably better over, you know, high rate UARTs, and it's basically made us a lot higher performance overall. So, so many thanks to Andy for his work on that. And I hope everyone appreciates the additional speed up that they're getting and less contention. Any questions on our change in UART handling before I move on? All right, CAN changes. So there's been a lot of changes in CAN in the last year. And now Sid has led this work, though it's also been quite a bit of work from other people, Tom Pittenger and myself, among others. But Sid's really done the lion's share of this work. And in particular, he's done a completely new HAL CAN abstraction and a test suite that goes along with it, which is really great to see. So that new HAL CAN abstraction made it much cleaner for implementing new CAN protocols. And so it's now possible to add a new custom CAN protocol with really what amounts to about a page of code or less. It's just you can instantiate a tiny CAN, you can basically subclass a CAN driver class and then just implement the parser for your new type of CAN packet, which makes it absolutely trivial to add a new custom CAN protocol. Whereas previously there's a lot of very complex work to handle all of the CAN events and the registration, etc. We also support CAN bus ordering, so you can now, if you've got a board where CAN2, you know, the STM32 CAN2 is logically your first CAN for your connector, you can make it the first one. You can have CAN2 and CAN3 instead of CAN1 and CAN2. And so we now support CAN3, whereas previously we only supported CAN1 and CAN2. On boards that have a third CAN bus like that, you can have, you know, you can have CAN2 and CAN3, for example, on a G4 board, which I added that support for that because I had a G4 board that had CAN2 and CAN3 on it. And as you saw earlier, I showed you some of the @sys logging. We now have a lot of CAN diagnostics showing up in the Sys File System, which is really useful for diagnosing what's happening. So basically, over the last year, we've seen a massive amount of CAN adoption, particularly UAV CAN adoption in the ArduPilot community. And it's really been pleasing to see. It was actually one of my major goals for the year that we would get wider adoption. And I've been delighted at the number of partner companies that have brought out CAN peripherals based around APPRF. There's been, you know, dozens of boards produced that are now out there in production use, which is really fantastic. Now, the next major step, as I mentioned earlier, and this is the question that Hamey asked, is about starting to support the higher data rate CAN. Because our H7 boards, as long as they've got the right transceiver on them, can do FD CAN, which means they can do sort of 5 megabit or more, even 8 megabit, depending on the transceiver, instead of the 1 megabit. And just as importantly, they can do much larger packet sizes. So FD CAN, you can do 64-byte packets, for example, instead of 8-byte packets. And so the overall overheads is much, much lower. It still uses 1 megabit framing, but the payload is run at the higher data rate. So it's the FDs is flexible data rate CAN, and it means that your data portion of your packet can run at a higher rate, which means the overall bandwidth you have is much higher. Now, it's a little bit troublesome mixing your CAN 1 megabit and the higher data rate on the same bus. There are some strategies for doing that, but they're quite tricky. And it is things that we're looking at possible strategies. There's two different routes we've got to take advantage of FD CAN going forward in ArduPilot. One is to adopt, so UAV CAN v0, the UAV CAN v0 standard, or v0.1 is often called, what it used to be called, you know, v0.9, and then it was like downgraded to 0.1, which was slightly odd. So it was designed for the 8-byte packets, right? So the standard is all around the 1 megabit 8-byte packets. And the UAV CAN v1, which is really just getting going at the moment, is designed to support the higher packet sizes. It can do both the 1 megabit or the 5 megabit, 8 megabit packets. and also the higher packet sizes. But it requires completely new packet definitions, protocol definitions, and it's a major disruption. So Sid and I are discussing two different approaches we can take to taking advantage of FDCAN. One is to support UAVCAN v1, and I do think we want to support that optionally in the IGPilot community. And the other is to do a v0.1 variant with supports fast data rates and high and larger packets, which would mean that that would be a easy upgrade for peripherals that are capable of doing FDCAN. And I'm quite keen on doing that because it supports all of our existing packet types just faster. And the new CAN HAL layer that Sid has done would make this very easy, because the splitting into the framing of the packets is done in one place in the CAN layer, which means it would be very easy to just have an option to switch that. And what I'd really like to see is have a CAN option that says, you know, auto detect if all of the devices on the bus are capable of the higher speed, and if they all are, then broadcast a message from the flight controller to say everyone switch to the higher data rate if this option is enabled. And that would give us a really nice way of taking advantage of the high data rates. So we'd also like to support UAVCAN v1, and I'm expecting that we'll do that over the next year. But it's slightly frustrating, the shift to v1, because we're just starting to see lots of adoption of UAVCAN in the community, and it's rather tricky, the v1 switch, as far as handling the bootloaders and handling the different firmwares you'll have to load. I'd really, on a lot of boards, I'd like to support dual stack, where it actually automatically determines whether it talks v0 or v1. And it may well do that by looking at what the DNA server, notice who the DNA server is, and then the DNA server, which is usually the flight controller, would make an announcement to say, you know, we would like to run v1. It is possible also, v1 has been designed to allow the mixing of v1 and v0 packets on the same bus, but I don't think that's been tested in practice by anyone. And so we'll have to just see how well that actually works in practice. So that's a sort of a bit in flux at the moment. And I'm sorry, I mean, you know, so vague in exactly what's happening with the high data rate CANs. And it's because we really aren't certain exactly how well all of this will really work in practice. But I'm expecting that over the next 6 months or so, you're going to see a lot of activity in this area. So stay tuned. The big advantage we do have is that because we've had high adoption of AP perif in the IGPilot community, if we enable these new features in AP perif, then it means that everyone's going to be able to get these new features very quickly with just a recompile and just rebase on the latest version, the latest release of AP perif, and then you end up with the new features. So that means that these new features aren't going to be quite as disruptive as they would have been otherwise. All right, any questions about CAN at all before I move on? And how am I going for time here? I think I've been waffling along for quite a while already. All right, let's move on. So AP perif, I'll just do AP perif very briefly because Tom's got a dedicated talk to AP perif. I was originally expecting my talk to be after his, but we rearranged the schedule a little bit. So we've had really good adoption of AP perif throughout the vendor community, which is fantastic to see. And it's been great, the feedback we've got from vendors. We greatly appreciate it. For those of you who don't know what AP perif is, I suggest you look at my talk from last year or look it up on the IGPilot site. Lots of new features in AP perif in the last year: ESC server output, including DShot, ESC telemetry, dual CAN support, MSP output, full AIM AP notify, and battery monitor support. It's really been a fantastic increase in functionality in the last year. And Tom's going to give you all the lowdown detail on that in his talk tomorrow morning. All right, Lua update. We didn't have a dedicated Lua talk this year, but Lua is actually one of the big things that's moved on, that's really been enhanced in the last year. And so I thought it's worth mentioning. there's been a massive increase in the number of Lua API calls. So Lua is our embedded scripting language that allows the ArduPilot flight controller itself to run, to asynchronously run a script or multiple scripts. And those scripts can interact via a very rich API with the rest of ArduPilot. And really the sky's the limit in terms of what you can do with Lua scripts. There's some fantastic examples, and if you're not familiar with it, I'd highly recommend you go and have a look on our YouTube channel for a bunch of great videos demonstrating some amazing capabilities with Lua scripts. But there's been a number of really fundamental changes in our Lua scripting in the last year since the talk by Michael Dubois, which really laid out the basis of Lua last year in ArduPilot. A lot of projects have started adopting Lua script to add new features. We've more than doubled the number of API calls, where I've got several hundred API calls now available in Lua. We now have support for Lua scripts baked into ROMFS. And this is something that a lot of people don't realize. You can actually take your set of Lua scripts that you want for your vehicle, and you can incorporate them into your build process so that the firmware that you distribute to your users bakes into it a set of Lua scripts. So this is ideal for things like Lua scripts that do something like, wind failsafe, where they automatically look at the wind state and the battery state to work out the endurance to get home, and automatically switch to RTL while you've got enough battery to get home with the known headwind on the vehicle. And this links in with the wind estimation talk that Paul gave earlier today. And so multicopters can now estimate wind, and you could combine that with the Lua script to automatically come home when you've still got enough battery to get home. Similarly, if you've got a tailwind, you can actually RTL a bit later and get a bit more time on station if you know that you've got a bit of wind assistance to get home. We've already got scripts like that for fixed wing in the Lua one, and you may want to bake those in. You might want to take a feature like that and build it into the firmware customized for your vehicle. And so you build a custom vehicle firmware for your particular type of vehicle, bake in the Lua script, and you build that into the firmware so that it doesn't rely on the SD card. So when the user swaps out the SD card with a different one, they still run the same Lua scripts. And this is absolutely critical. If you want those Lua scripts to be flight critical functions, then you really need to do that. Some highlight other features that have come in the last year. We now have much more extensive mission control, and there's some great examples from Buzz in particular on how to create complex missions and modify missions on the fly using Lua scripts. Much richer access into our AHRS functions for IMU and attitude state estimation data. Lua script access into the proximity data for making decisions about proximity to objects and object avoidance. You can write I2C drivers in Lua now, so you can actually go and access the registers on an arbitrary I2C device and add support for sensors that ArduPilot doesn't have in the main firmware, which is great if you've got something like an I2C humidity sensor or radiation sensor or similar that you want to build in. You can write a Lua script to write that driver as a script, then bake it into ROMFS and get it to start reporting data down to the ground station or into the log. Analog input, PWM sources for pulse width sources and GPIOs, and that's just a small sample of some of the new APIs we've got. There are literally hundreds of new APIs that have gone in the last year. So really fantastic work that's been right across the dev team. We've got new APIs from a dozen or more members of the dev team, and it's been really great to see the blossoming of the Lua ecosystem within ArduPilot. So any questions about the Lua updates? All right, new IMUs, a lot of new IMUs supported. The ICM4 XXX 4XXX, these are the variants. I'm really excited about those. and they're a major upgrade from InvenSense, and I'm looking forward to vendors starting to incorporate those ICM4 series IMUs in their products. They can, of course, use the HWDF system if they're thinking of it as a future upgrade. They might like to add it in as a automatically detected IMU now, so that if and when they do start including that new IMU on a future update, that it would then be automatically detected. These new IMUs offer a major upgrade in terms of lower drift, better cross-axis, less cross-axis coupling, and much faster sample rates, lower bus utilization, lots of nice advantages in these new InvenSense IMUs, and much better APIs. So really nice to see that as an enhancement. We also support the new ADIS IMUs. I might have one of those here somewhere. There's one. So this is one of the ADIS IMUs. This was on an MRO board. And that big white lump there, like a sugar cube, that's an ADIS IMU, very high quality, quite expensive, but very high quality IMU. That's also in the CUAV X7. So there's a CUAV X7 board, and the reason why it's so tall here is to incorporate that much larger IMU. So there's these very high quality IMUs are now supported by IGPilot. And the third type of IMU we've got, really big one in the last year, is external IMUs. So I've got a photo down here of a vector nav, and I've got one on my desk here somewhere if I could find it. So that's quite an expensive, that sells for, I don't know, $3,500 to $4,000 US, I think. And with a high quality IMU, plus it includes a full AHRS system, so, you know, state estimation, etc. And we fully support that. We can use that either as just an IMU, or we can use it as an IMU Barrow GPS, including GPS heading, or we can use it as a full state estimation, and we can actually have it in parallel with the onboard EKF2, EKF3, and run them in parallel. And then select, in flight, you can actually flick between the different state estimation systems. So you can run it as a ride along if you want to. That's a fairly major change at IGPilot, and I'm expecting more external IMUs to support it in future, more serial connected IMUs. There's already a number that are candidates that are being looked at by various people to support more of these very high-end IMUs, and looking forward to somebody doing a fiber optic gyro as an external on IGPilot. It should be quite easy to add one of those if you can afford to buy it. And of course, I'd be very happy to develop a driver on a fiber optic gyro if somebody wanted to send me one, a serial connected FOG.
Hey,
any questions at all about that?
We had a question from YouTube.
Oh, yep.
Does AP-perif support Lua?
Actually, interestingly, so embedded Lua scripts inside AP-perif is coming. There is actually a branch that's been developed that has Lua scripts within AP-perif. The current releases of AP-perif and current master AP-perif does not run Lua scripts, but it is coming. Now, the people who have done that work, I don't know if they're happy for me to reveal who it is, but if anyone on the call is happy to put their hand up and say that they're the ones that have been doing it. Anyone?
Good. All good. Talk about
all
it.
Good. Okay. Yes. Thanks, Philip. Yes. So I can reveal that Hex has been with Sid and Michael and have been doing that work to support AP-perif inside, Lua scripts inside AP-perif peripherals. And which means you can do, for example, you know, on the trivial end, you can do very fancy LEDs inside a peripheral. But of course, you can do a lot more serious work as well. And so that's a fantastic addition. I'm looking forward to getting that in. But that is still being developed, and I'm expecting that in the coming months, you will see Lua scripts inside AP-perif, particularly baked into ROM-FS inside AP-perif would be the typical way of doing it rather than on an SD card.
Cool. We also have one other question that's just come through. AP-perif IMU.
AP-Proof IMU is coming.
Like the VectorNav, but
indeed. So AP-Proof IMU is coming soon because I have a board with an AP-Proof based board with an IMU that is actually in the post to me right now. And but I could also, of course, prototype it on any of the existing flight controllers that support a build as an AP-Proof, like any of the MRO PixRacer Pro, the Cube Orange, any of those can be done as an AP-Proof. So yes, IMUs in peripherals is coming, but this will become important as far as bandwidth with FD-CAN, because an IMU, depending on how you're using it, if you're using it for sensing vibration in a motor, for example, say you've got this built into an AP-Proof ESC, which is also coming, by the way, ESCs, AP-Proof ESCs are coming. So if you've got it built into an ESC, then you might like to use the IMU to detect high vibration for pre-fail detection or logging and post-flight analysis on your ESCs. Now, if you're doing that, you're going to need very low rate. You might have like the RMS vibration coming back at sort of 5 hertz, 10 hertz or less. But if you're using it to actually as a input to your state estimation, your attitude control, then that means you need that IMU data at a much higher rate, and that means bandwidth. And this is where the high rate FD-CAN support is going to be so important. And that's where the work that Sid is looking at soon for high rate FD-CAN support, both on V0 and V1, is going to be the enabling technology to enable the high rate IMUs on CAN bus. So any more questions on the IMUs before we move on?
Yeah, Olivia's just posted another one that came in through YouTube. They've asked, with regards to the external IMU, does this open the door for having multiple controllers linked rather than just the external one?
Yes, and potentially. At the moment, we don't have a way. We do have a piece of code that can output the VectorNav protocol, but we only did that in our simulator. We've got basically a VectorNav VN300 simulator. Now, we haven't yet done the work to move that into our code, a bit like we've done the NMEA output. So those of you, I mean, if you're familiar, that you can just set a serial 5 protocol equals and then the right number for NMEA, and any UART in ArduPilot can become a NMEA source, right? Which means it essentially becomes like a GPS for another system. It would be really nice to be able to set a, serial 5 protocol equals a external AHRS protocol, and then you could have that as an input to another system. The main question is the handling of the latency of that, but it is doable. It should be doable via both CAN bus and via a serial UART. And so yes, I expect we will support this in future, but right now we don't have the generation functions for that in ArduPilot Master. That's an upcoming feature. If it is an important feature for you and you'd like to see it pushed up the priority list, then please open an issue, or if you're a partner or a vendor and you want to help fund that work, then feel free to get in touch with the developer to push that along a bit faster. But that is going to be coming because that's on my roadmap of things to do in the coming months. Any more questions there?
Nothing from YouTube at this point.
All right, so I'll move on.
Last one though, Tridge, it was more about redundancy or distributed flight control, more so than...
Yeah, and there are some vendors who are actually flying in production distributed flight control. There's some with multi-rotors, for example, and they've built up custom systems utilizing the existing capabilities in ArduPilot, then extending it. And critical components of that is things like the standby mode that Leonard added for Copter, which is really important when you're doing, a redundancy between flight controllers. It would be really good if we gave a bit of a how-to in our wiki on how to build a redundant flight controller system with ArduPilot. It is doable now because a number of vendors have done it and are flying it in production, but it is a bit of a black art in terms of how to get all of the pieces in place. But these types of output protocols and campus protocols are an important part of this. Yes, hopefully over the next year, we'll start developing the key pieces to make that easier to do and start to document how to do that. And we'll get more people running redundant flight controller setups. All right, so diagnostics and error handling. So we are coming near to the end of the talk for those of you getting systems development fatigue. There's been a lot of improvements in diagnostics and error handling in the last year, a huge expansion in the AP internal error system, particularly from Peter Barker and also Michael Dubois and others. So we now have source line numbers when we generate an error. So tell us exactly, what line of code generated the error. And we have a much wider range of errors reported, which is really useful for log analysis. We've got a huge number of improvements in the area of detecting and preventing stack overflows, which is really nice because we did for a while there, we were a bit low on stack and we got a couple of flight controllers hitting stack overflows. And so that's been fixed up and we've got much better diagnostics on that now. We've got a new memory corruption detector, which is a compile time option, but very useful if you are getting any memory corruption, which is always a possibility in a C++ project. So we've got optional guard regions on memory allocations, which is very useful for detecting memory corruption. If you want to use that, then you should probably talk to me about how to enable that and use that. We also have a new storage backup restore system. This was part of there was an issue with some flight controllers, in fact, quite a few flight controllers with corruption of storage. And so we now have an automatic backup system for our storage if you're on FRAM. If you're on FRAM and you're on F7 and H7, we do it. And then we automatically restore the corrupted parameters. We do flag an internal error at this stage, but it means that you don't lose your parameters. And that's been one of the more annoying issues we've had over the last year. It was very, very difficult to track down. And I'd like to thank all of the vendors who participated in the diagnosing and assistance with that, particularly HEX and CUAV. Both were heavily involved in diagnosing and dealing with ways of dealing with that particular issue. All right, so final slide. So there's been a lot of changes and we're now ready for the 4.1 release, and the PR for Rover 4.1 was opened yesterday, I believe, by Randy. We're expecting the first beta releases of 4.1 for Copter in the next week or two, and then probably Plane shortly after that. Quite long beta period we're expecting because there's been, as you've seen from this talk, a lot of system level changes, and there's been a lot of changes in other areas of the code. So we really need people to jump on these beta releases and test them. So when the betas come out, please get testing and, more importantly, reporting both positive and negative experiences with the betas, including logs. Please fly with replay logging and log disarmed if you can for better EKF analysis. So really, everyone, hope you enjoy the 4.1 release. It's been a long haul, but really worthwhile. And thanks to everyone that's done the testing on the 4.1 alpha, the latest releases over the last few months. And happy flying to everyone. Enjoy the RG-Pilot experience. So any final questions before we wrap up? All right. So, well, if there aren't any more questions, then I think we've probably had enough questions with this, and we've gone on rather long, the talk. So what we'll do is I think we'll maybe take a couple of minute break now, and a sort of a toilet break and a coffee break. So come back in a couple, let's say 5 minutes. We can have general chatter between people if you don't need a toilet break, and otherwise come back in 5 minutes time. And we'll actually then be on schedule actually for the next talk. So, so see you all in a few minutes time, and we will, our next talk that we have, I'm just looking up what our next schedule is.
Yeah, it's me.
Third talk is Randy Mackay with the GPS, non-GPS navigation transitions. So We'll start at the top of the hour, I think. We'll start on that talk. And meanwhile, developers can chat among themselves. Thank you very much. Right, I'll switch back to my other computer. And so that audio coming through okay?
Yep.
How are we doing on the live stream? Any questions there? Oh, thanks, Ian. I just saw a comment from Mad Tech, Ian. Thank you very much. Everyone feel free to unmute and chat if you'd like to during this time, if you're not off on a toilet break. And you can turn on video and things to be sociable. Hi, Randy.
Hello. That's a great talk.
That keeps
You're
things a
both
bit more
great.
entertaining for those on the live stream.
Yeah.
But many of them, I think, might have been going off on toilet breaks as well.
We'll see
G'day,
if I can
Peter.
not even sure if my audio is unmuted. Maybe. Any audio?
Yep, we can hear you.
So I guess what I'm playing with.
Oh, you don't have any audio, Peter.
Really, I can hear him. I can
At
hear him.
least, oh, maybe I know why. I probably do have audio, but I've just got my speakers turned off on this system.
Peter doesn't have any audio.
My apologies.
Sorry, do I have audio at the moment?
You do have
I
audio
think
now.
you
My
do.
apologies. I had the speakers turned down because of when I was
No, Peter,
presenting from the
you
other
don't.
computer.
You don't have audio at the moment. No.
Thanks, Tom.
I think Tom is yanking your chain.
So just taking a little bit of time to start working on a linchpin frame. So vast amounts of carbon fiber tubing.
All right, very good. The lag on the live stream seems to be quite low, which is great. It seems to be only like 15 seconds or so.
Well, the internet's good in my area because all the kids are back at school.
Yeah, okay.
When we
After
had the whole
lockdown.
lockdown thing going, the internet was terrible. They're all watching Netflix.
Yeah.
They're supposed to be
And
doing their
like Fortnite.
homeschooling, I'm told.
Not my kids. They're out working.
They're working hard. Excellent.
You got him out digging ditches again, Leonard?
Moving
I've got
blocks.
Connor doing. He's now mowing all the lawns and stuff like that. So yeah, suitably working hard. And the kids. Oh, we've got 3 kids. Each of them do a different dinner each week. So that's good too.
Man, that is so good. Yeah. What's the old saying? The devil likes idle hands.
Oh, mate, it doesn't stop my kids.
The problem I had with my kids doing the mowing is I didn't distinguish too well between small things that have been planted in that you wanted and things that you
Right.
Actually, Lee's done a really good job of that, teaching the kids which plants are which in the garden, and
I torture them with it.
yeah, and so she can send them out to get the herbs for the meal and stuff.
Great.
Hey, Tridge, have you decided that my face isn't fit for video or something?
No, you should be able to turn it on. Sorry. See.
You cannot start your video because you're too ugly on my thing.
Do you want to try it now? There you go. Yeah.
Church, I think Leah's done that.
Can you turn it off?
Could you give us a little warning at least?
Yeah, it's like, yeah, Leonard, face for radio, you know.
Could be worse. You could have a voice. You could have a face for radio and a voice for mime.
Are you
Yeah.
saying he doesn't?
All right. So, okay. So I think we can now start on the next talk. So the talk we have coming up is very exciting, from Randy Mackay, and so Randy is our copter and rover leads, and also is heavily involved in avoidance work and other aspects of the code. So today, Randy's going to be telling us about GPS and non-GPS navigation transitions. All right, over to you, Randy.
Thank you very much. I will just start sharing my screen here. Let's see if we can do this. Okay, hopefully you can see that. We'll go to.
Yep, all good.
presentation. Okay, so thank you very much, all. My presentation is around EKF source switching, which is really the new features that we've added into EKF3, which can be used for various purposes, but primarily it's used for transitioning between GPS and non-GPS environments. So here's a little agenda of, oops, just want to move this out of the way here. Little agenda of the talk, so you know what's coming up. So yeah, first of all, just a couple of example videos. Then I'll go through the setup and testing in case you want to get this working yourself. Then I'll dive into a little bit of detail on how it works. What EKF changes we made. Also the scripts that we use and how they decide which source to use. And then a little bit of detail on alignment and resets, which makes the transition smooth. And then finally, simulation and some of the future plans and improvements that we are thinking about. Of course, just jump in anytime if you've got a question, just unmute and ask questions. So first off is a video of Rover. And this is my garage in case it matters. And this is the Ion Robotics rover. It's got a couple of GPSs and wheel encoders on it. And that's what it's going to be using both. And inside of my garage, I actually do get a GPS lock, but it's not very good. So what you'll see in this video is it transitions between the use of wheel encoders and heading and GPS for its position estimation. I guess I should also say that the way that you can tell which sensor it's using is by a beep. So if it beeps once, it's using GPS. If it beeps twice, then it's using wheel encoders. So it starts off using wheel encoders. It has chosen wheel encoders automatically. Arm. It's a very simple back and forth mission. It's just 2 waypoints. Just switch to GPS. Switch to waypoints, it'll turn around and come home. All right, so that's the first example using wheel encoders and GPS. The next one is Multicopter. Now this actually was taken before the rover video that we just saw. This is actually middle of last year. So at this point, we didn't have the automatic switching between sources. So I'm going to be, in this video, I'm manually switching between GPS and an Intel T265 3D camera. But I just want to make sure it's clear that the automatic switching does work in Copter as well now. So here it is taking off in loiter with a GPS. This is my regular QPilot quad with the Intel camera on the front and the GPS sticking up. Then I've just switched it manually using an RC switch on the transmitter to switch it over to the camera. And I fly it under this concrete canopy. And I'm rotating it with the yaw stick. And you can just see how stable the position is. You wouldn't get that kind of stability with the GPS underneath that canopy. Then I fly back out and switch it back to GPS again. So yeah, I guess the key points here to look out for is that the vehicle is stable even without GPS. And also that the transitions are very smooth. So, if I didn't tell you that it was switching sensor sources, you wouldn't have noticed. You wouldn't have seen a twitch or anything like that. And those are the key challenges of this project. Oops, we don't need that. Okay, so next, I just want to go over the setup in case you want to set this up yourself. So you need to use RGPilot 4.1 or higher. Any of the vehicles should work. So I've used Copter and Rover, but presumably plane would also work, or submarine or whatever. You need to use the EKF3. So that's enabled by default on 4.1. So you shouldn't have to do anything, but just in case, the two parameters you have to set are the EK3 enable and AHRS EKF type. Set those. You also should have made sure that the 2 or 3 sources that you're going to use work. So follow the instructions on the wiki for example, setting up the wheel encoders or the Intel T265 camera. You have to follow all those instructions to to make sure that those work. So then next, inside the EKF, we've added this new APNav EKF source object, and it allows you to set up 3 sets of sources. Each source would be used for like a different environment. So for example, the first set of sources would normally be set up to use GPS. It's totally arbitrary, but the way I've been doing it, the first set is always the set that uses GPS. So you say that the first sensor set is going to be using GPS for its horizontal position. So source 1, pos XY, set to 3 for GPS. Same for velocity. Horizontal velocity, use GPS. For vertical position, you might use barometer, which is 1. For vertical velocity, again, GPS. And then for heading, we use the compass. So that's your first set. Then for your non-GPS environment, normally it's set up the secondary set to use, for example, horizontal position, velocity from the external nav system, which is, SLAM or the Intel T265. You could get the vertical position as well from the camera, but actually it's sort of a bit of a special case with the Intel cameras. They're quite sensitive to vibration. So if any axis goes wrong, it's usually the vertical axis that goes wrong. So for that reason, in my tests, I've very often been sticking with the barometer with a rangefinder as well to help keep the altitude above terrain stable. And then for the yaw, I've tested both ways. You can set it up so that source 2 yaw is the camera or the compass. Either one works. You can take your pick. I often use the compass though. Also, by the way, just at the end, at the bottom of each one of these slides, you'll see a link to an appropriate page on the wiki. So, in case that there's more details on the wiki there that you might want to check out. So right, so yeah, just to clarify, you set up these different sets. You don't specifically, we don't dynamically, for example, change the first position source between camera and GPS. We don't do it like that. You set up different sets and then you switch between the sets. And the way that you switch between the sets, well, there's a couple of different ways, but you can do it manually by setting up an auxiliary switch. So for example, on my transmitter, I have a little turning knob on channel 6. So I set that up as my EKF position source, which is 90. So I set RC6 option to 90. And so the low position selects GPS, the middle position selects the camera. And in some of my tests, I had a third position, which was actually optical flow. So that allows the manual switching. For automatic switching, we do that via Lua scripts. So we set up, I'll jump into the Lua script details later, but you set up RC7 option as 300, which is, an option reserved for scripting. And then the script will go in there and check what the position of your, auxiliary switch 7 is. So if it's low, the script doesn't do anything. If you pull it high, the script starts automatically selecting which source set should be used based upon various, based upon the status of the EKF and also, some feedback directly from the sensors. Also, if you're using external nav, like Intel T265, you might want to set up a third auxiliary switch to be 80, which is for the BISO align. It means realigning the yaw of the camera to match the HRS. So these cameras, their heading is a bit arbitrary. So if you point it south and then power up the camera, it will think that 0 is south. So to allow you to realign the yaw of the camera with, say, for example, a compass, you might want to use this, this RC option 80 does that alignment, so you can manually align them. It will also actually align them at startup. So you might not need to have manual realignment, but in my development, I've always had that switch available, and after a longer flight, I've realigned them. So the next thing you need to do is actually install one of the Lua scripts. If you want automatic switching between between sources, you need to use a Lua script. So I've written two. One of them is called AHRS source.lua, and the other one is AHR source GPS wheel encoders, and you can imagine the difference perhaps. The AHRS source GPS wheel encoders is of course for vehicles with GPS and wheel encoders like the rover I showed in the first video. The AHRS source .lua script was actually for the multicopter, and that supports, that's for use with GPS, external nav, i.e. TT65, and optical flow, those three sources. Then what you do is you may need to manually adjust some of the thresholds that the scripts use for deciding which sensor set to use. So these are all a bit arbitrary, but these particular scripts use these three parameters. The SCR user 1 is used for the rangefinder threshold. So below the rangefinder threshold, it may use optical flow. It certainly will not use optical flow if it's above that rangefinder. The next one is for the GPS accuracy threshold. And so this is the speed accuracy. I should be clear on that. This is actually, during the development and testing, we tried various different outputs of the GPS as the basis for making the decision. We tried, H-stop, satellite count, a bunch of things. But after a talk with Paul, we tried at the speed accuracy, and this was by far the best. So we found that a value of 0.3 works well, somewhere in that range. And then the last parameter, SCR user 3, this is for the external nav vertical velocity innovation threshold. So coincidentally, this number is also 0.3. What that means is that we're going to be using the external nav potentially if the sensor data agrees with the EKF estimates for vertical velocity within 0.3 meters per second. Yeah. So those are the three criteria that we use to do the switching. So after you've got that all set up, you should definitely test it. Don't just go straight into automatic switching. Take a couple of easier steps before you do that. So for example, first manually control the switching of the sources using the auxiliary switch, and test fly the vehicle in the GPS and the non-GPS environments and make sure that it's flying well in each. Sometimes, for example, when you're using the TT65, you run into problems with high vibration, or you might have the camera's heading might not align with the compass, and you set up the sources to use the compass as the heading, and then you'll get these toilet bowling or worse. So again, just make sure that you've manually flown it in both the GPS and the non-GPS environments and make sure that it works. Then what you do is you enable the automatic switching and then manually carry the vehicle from one environment to the next, and just make sure that those thresholds that you've set up are working properly. You should find that it switches within 2 seconds. If it doesn't, then maybe those thresholds need some modification. And then finally, after that, try driving or flying it between the two environments in a semi-manual mode, or semi-autonomous mode like loiter, just to confirm that the transitions are smooth. And be ready to take back control in either stabilize or alt hold. Normally I would switch back to alt hold, but if, for example, you're using the T265 and you've got, especially if you're using it for the vertical position, if that camera goes nuts, again, normally because of vibration, switching to alt hold may not save the vehicle because it might rocket into the sky. So in those cases, get ready to take over in stabilized mode. Is that clear? Cool, I'll move on then.
I have one question, Randy.
Sure.
How are you setting home when you're starting, like, for example, with encoders, and then you switch to the GPS one?
Great, thanks. Yeah, the ECAP has been slightly changed. You can, so there's a couple different ways to do it. One is that you can just, arm and take off outside and then move inside, or you can, bring the vehicle outside, switch the source to GPS and let it set its home out there. And then move the vehicle back into the non-GPS environment. That's the easiest way. The other way that you can do it is if that's not an option, you can of course start the vehicle up in with the non-GPS source set, and then you can actually right mouse button click on the map and tell ArduPilot where it is, and then the ECAP origin and the home will both be set to that location.
But what happens then when you move out, and if you set it up, like if you set the home wrong, and then you go out?
Yes, this is a very good point. This actually comes up on the very next slide, I think, as one of the known issues, because you may find, and in fact, I did actually find in some of the testing, especially with Rover, if you set the home indoors and it's off from reality, and then you move outside, and then you get the real position according to the GPS, it will shift the position, and it will essentially shift home. So when the vehicle returns back to the non-GPS environment, maybe to RTL home and land, it can end up landing at a different position than it took off from, and that's because of the way that we handle the transitions and the offsets between the two. So far, I don't know of any solution to that problem. Is that okay?
Yeah, that's fine.
We can talk about it a little bit more later, maybe too. It really depends a little bit upon the. I think the solution could depend upon the SLAM system that you're using. So if it's perhaps Google Cartographer, which keeps a 3D map in memory, and when it comes back to a known environment, it will reset itself. We could perhaps deal with that differently than if we're using the T265, where it doesn't really maintain a full 3D map. If it goes outside and loses its position estimate and then comes back inside, it doesn't recognize again, oh, I'm back where I started. It won't. So yeah, we might have to have different solutions for different systems.
There's a couple of other questions in the chat.
Sure.
Can it be switched via MAVLink?
That is also on an upcoming slide. That is in the future enhancements area. We cannot change it. We cannot change the source set by MAVLink, but it's not a difficult change to make, not a difficult enhancement to do. So I suspect we'll do that in the nearest future.
Actually, it's an RC channel option to switch them, isn't it?
It can be an RC option, yes.
Well,
yeah,
we actually do it in. Pretty sure we merged that thing in master, which allows you to trigger RC channel options via MAVLink. So it might actually work now.
Okay, cool.
Second question was, does it align with a yaw reset?
Yes, it does. Yes. So yeah, one of the difficult parts of the project was handling all of the resets. So position, velocity, and yaw resets. It does capture those, catch those, and deal with them as almost as well as we could. There are still a couple of enhancements that we could do, but mostly it handles those.
And the last one here was, can we use dead reckoning until we get GPS?
Can we use dead reckoning until we get GPS? So I'm not sure I totally understand what that means, but I guess one common question that we get is, can we fly with IMUs only if we lose GPS, or if we lose any any position source, whether that's you know, a SLAM camera or beacons or what have you. And the answer is always just that, you know, with the quality of IMUs that we have on most autopilots, you know, which are very similar to the IMUs that you have in your cell phones, your smartphones, you know, the drift is so high that we very quickly get a massive velocity, and then you know, a very quick position move, or sorry, the position estimate starts drifting off very rapidly. So you really have less than 10 seconds or so before before you have an unusable velocity in position. So yeah, IMUs alone, if that's the question, IMUs alone are just not enough. We need to have some kind of absolute or local position source.
All right, thank you.
I guess maybe the question was a little different. Right, seems like you could say, well, I've got GPS now and I travel 10 meters, so home is 10 meters back that way. Yeah, I think essentially, if I understand the question, I think that essentially that is what it does. So let's cover that a little bit more when we get to the transition section later in the talk. Okay, so next I'd like to dive in a little bit to the EKF changes. Now,
Randy, I have a question.
Yeah, sure.
Yeah. How does optical flow, like just standalone optical flow, come into play at all on this?
So
or does it?
It does. It does. So you know, optical flow provides not an absolute position. It provides essentially a horizontal velocity. But you can integrate that velocity to come up with a position estimate. And you know, getting back to the previous question about using IMUs only, optical flow velocities are enough to keep the drift and noise from the IMUs under control for the most part. So at least for, you know, if we're talking about time periods of, you know, a couple of minutes or so, the optical flows, you know, can give you a good position estimate. And you know, in terms of this, you know, wider feature of, you know, GPS and non-GPS, it will work with optical flow and GPS only. Like, you don't need to have a fancy camera for this feature to be useful. Is that even close to answering your question there, Tom?
Yeah, I'm just picturing for a fixed wing version where if you have a GPS going in and out, because normally you'd rely on the dead reckoning, but I'm just wondering if any of these settings actually would help if you had you know, optical flow, if it doesn't enhance that.
Absolutely. So you can definitely set up these sources so that you're switching between GPS and optical flow. That'll definitely work. And you could you know, write a little Lua script, which then looks at, you know, maybe the GPS quality, or, you know, even the status of the GPS. And if you lose your GPS, you change the source over to use optical flow instead. And I think the EKF would deal with that. It would stop looking at trying to fuse, well, it would stop trying to fuse the GPS data and only try and fuse the optical flow. So that could work. And just do it when you're low enough.
Now, in the event of optical flow, it does move back to a GPS if you do get that. I'm not sure if I followed that on your talk. So for source 1, source 2, like how well does it switch back?
Well, yeah, again, it depends upon how well the Lua script is written. So the Lua scripts that I've written so far, one of them, which does include, you know, switching between GPS, T265 and optical flow, it does have some decision making, trying to decide, you know, which one is best, and it'll switch in either direction. It doesn't just go, you know, just from non-GPS to GPS and never back again. It'll switch back and forth, you know, depending upon a bunch of criteria. So I'm sure you could write a Lua script which would intelligently switch between GPS and optical flow. And you can
gotcha. Okay. Yeah, thank you.
There's also, actually, I didn't mention it on this slide, but you can also blend both GPS and optical flow at the same time. You know, that's a feature that's been in EKF for a very long time. Paul added that and demonstrated that at a developer conference a few years ago, where he was flying a copter underneath a tree. That all still works. There is an EK3 source options bitmask parameter, and one of the options in that is fuse all velocities that are in any source set. So, so what you do is you set up, your regular GPS source set, and then you set up a second one which has optical flow listed as the velocity XY source, and then check that that option bit, and then it'll fuse not only GPS velocities but also optical flow velocities, whenever they're available. Is that okay?
Yeah, awesome. Thank you.
Okay, so yeah, next is just diving into the EKF a little bit. Now, a little disclaimer. Obviously, I'm not the EKF expert. Both Tridge and, of course, Paul know a lot more about the EKF than I do. But I learned a lot about the EKF as part of this project. And I just wanted to pass along some of my increased understanding of the EKF. But these slides have not been run by Paul, so you can probably point out a bunch of things that are wrong with it. But my simplified view of the EKF is on these slides. And I hope that it helps other people, other developers, who maybe are hesitant about jumping into EKF because they're worried about all the complexity. Seems like the scariest, most complex system that we part of ArduPilot, but that's true. But there's also parts of it which are very understandable. So I'm hoping that more developers will get involved with EKF development, because it's not as bad as you might think. So with that disclaimer put to the side. I think the EKF has like at least three components. So it has this interface, component at the top here in orange, which we're all familiar with. This is, where you get your, your attitude or your position or whatever. So that's really quite easy, and everybody understands that part. Then there's this measurement section. And this is where we take in all of the sensor data and we push it into little buffers. So we have IMU buffer, GPS buffer, external nav buffer, barometer buffer. You have all these little buffers that we push the sensor data into, or sometimes we pull data from the sensor into these buffers. But in any case, the sensor data ends up in these buffers. And you can actually see how, there's a little link here, this little C code link. You can just have a little peek at that if you want. And you'll see that it's not too bad. I'm not sure how I'm doing for time, but I'm actually going to click on it and show you. So for example, this is the right, this is probably very small. Maybe that's a little more visible. Right external nav data. So this is what gets called by the AP visual odometry library to push position, attitude, and expected error data into the EKF. And right, so bunch of vectors, 3Fs come in. We do a little bit of checking of the timestamps to make sure that they're not too close to the last timestamp, so we don't get an overflow of data. And we add we do a couple little things, but eventually we just push it into a buffer right here. So it's really not too. That part is not too scary. Then, right, you might ask, why do we have these buffers in the first place? What's their purpose? And this is really just to deal with the varying lag between sensors. So GPS, tends to have quite a long lag. IMU has incredibly short lag. The barometer is sort of somewhere in the middle. And then finally, there's this fusion step. And this is the really complex part. And I don't understand all of this. But I guess I understood it enough to add in this little layer here, which is the source selection object that I mentioned before. This is the object that has those, parameters that I talked about earlier. And previously, on every iteration, the EKF would come through and it would check if there's any data from any of the sensors which are at or before the delayed time horizon. It would check for any data and then it would start fusing them in. What we've done here is we've added in a little check. So it still pulls the data in from the GPS on if there's any data there. It definitely pulls it in. But then before it goes to fuse it, it just checks with the source selection. Hey, is my active horizontal position source the GPS? If yes, then it'll fuse it as per normal. If not, it'll just ignore it. Basically just throw it away. The other thing it does is it checks if the source has changed. So if on the previous iteration, the source was external nav, and this iteration, it is GPS, then it triggers a reset. So you'll see it sets a reset flag if the source changes. And again, there's a link to the code there if you want to have a peek. And finally, the last change that we made is on the calculation of the innovations. So the innovations are a useful input to the Lua script's decision-making as to which source is best. So even though we might be ignoring the GPS data right now, we still want to know, how closely the GPS sensor data is matching our estimate. So even though we don't fuse every single source, we still want to calculate the innovation for every single source. Is that clear? Cool. And just as a side note, the EKF has these two time horizons, these two times that it deals with. There's the delay time horizon, which is sort of in the past. That is in general the now minus the longest, the most laggy sensor's lag time. So like it might be 0.2 seconds or something like that. So that's EKF is fusing data in the past. And then what it does is it projects forward. So it takes that delayed estimate, and then it essentially sort of extrapolates forward using the IMU data, which we've collected up between that old time and now. That's a bit of a side note. Doesn't really matter too much in terms of this project. Okay, moving on. Okay, next is pretty simple stuff, actually. This slide covers how the scripts make the decision between which source to use. So the more complex script is this, AHRS source Lua script, and it has to decide between the three sources: GPS, external nav, and optical flow. And the way it does that is it breaks the decision into two. So first, it's a GPS versus non-GPS. And then it's going to be deciding, if it's non-GPS, it's going to be deciding, should it be external nav or optical flow. So it has two votes, basically. So on every iteration, it's voting at these two different levels. And it updates these vote counts at 10 hertz. So each time it will make a vote, +1 to GPS, +1 to optical flow. So it'll be doing these two votes on every iteration. And it will switch source if either of these two vote counters reaches 20 in either direction. So essentially, sort of cumulative 2 seconds of data suggests we should go this way, we'll switch. So it also means the decision making will never happen in less than 2 seconds. Now, a little bit of detail about the GPS versus non-GPS vote. So like I mentioned earlier, it'll use the GPS speed accuracy. So if that's good, or the GPS is usable, which means that it's basically got a speed accuracy of less than 1, and the non-GPS is completely unusable. So for example, on the next line, you can see here, is the non-GPS usable or not? It checks this. So non-GPS is usable if the external nav vertical velocity innovations are less than or equal to 0.3, then that means the camera or the external nav is usable. Or if the rangefinder is low, if we're below that rangefinder threshold, then again, the non-GPS is usable. So if neither of those two are true, it's going to switch to the GPS. Then when it comes down to the external nav versus the optical flow decision, again, it uses the external nav velocity innovations. If they're low, it'll vote towards the external nav. If they're high and the rangefinder distance is low, then it'll vote towards the optical flow. So that's all the logic that we're using. Any questions or comments? Anybody want to point out the glaring hole in how we use optical flow? So right now, the optical, you might notice here, it's only using the rangefinder. It's not actually checking optical flow velocity innovations. It's not even checking the status of the optical flow. So there's definitely room for improvement here. Is that cool?
Well, what you said about the rangefinder on it. What if you're out of range, like on a plane?
Yeah, so in this script that I've got, if you're outside of if you're above that rangefinder threshold, it will not use the optical flow at all. It'll leave the source back on the GPS and try and use it. That doesn't mean that it's going to fuse bad GPS data though, because this whole change is really just turning on and off the faucet for this data to flow into the EKF. After that, the EKF will still do all of its regular checks upon the data to make sure that it's not too noisy, that the innovations aren't too high, and all those regular checks that it would normally do. It's just sort of turning on and off the faucet. Is that cool?
Yeah, I guess I'll look forward to playing with it.
Cool. Also, I've talked about innovations a bunch of times, and I just wanted to make sure that people understood what innovations were. I mean, I think I already sort of explained it on the last slide a little bit, but here's a little diagram to try and explain it a little bit further. So my understanding is that every iteration, the EKF builds upon the previous iteration. So it had a position estimate, an attitude estimate, et cetera. Then it adds on to that the latest IMU data to come up with a new predicted estimate of all kinds of things. But in particular, for this project, the predicted velocities are the key. So the IMU comes up with these predicted velocities based on the previous estimate plus IMU. And then we have this incoming velocity, say from the external nav system. And the innovation is simply the difference between that latest velocity from the camera and this estimate. That's it. So pretty simple. Okay. Onwards. Okay, so this is the slide, I think, which gets back to some of our earlier discussion about home moving, etc. This slide is really talking about, the alignment and the resets, which was, a difficult part a challenging part of this project. So we really wanted smooth transitions. And to get smooth transitions, you need to either avoid any jumps. So you need to make sure that the two sources are producing the same numbers or very close numbers. Or if they are jumping, you need to be able to handle those jumps. And we had to do both of these things. So to avoid the jumps, we've added this align inactive sources method. And again, you can click on it to have a look at it. And this is inside of the new source, APNav EKF sources class. And this is called by the EKF at the end of its fusion step. So after it's come up, it's fused all the data, et cetera, it's just about to exit. Just before it exits, it calls this method. And inside of this method, it checks what is the active source. And if, for example, the active source is GPS right now, it will then call over into the visual odometry library, which is used for external nav, and say, hey, update yourself to match the HRS. So if the HRS is using GPS right now, it calls over to the external nav basically and says, hey, align yourself to the HRS. So align yourself to the latest EKF estimate. So inside the visual odometry library, it then moves its position. So for example, in this little picture here, the external nav is off from the GPS a little bit. It's a little bit rotated as well. It will shift its position to match the HRS, which is based on GPS. It should actually also realign, I think. It should probably realign the yaw at that moment. It doesn't. Very simple change. I haven't done it yet. I'm planning to do it, but at the moment it doesn't do that. So right now that yaw alignment is only happening at the when the pilot triggers it using that auxiliary switch. Okay. Next one is handling of jumps. So the EKF and HRS already can tell a caller if there's been any reset in position, velocity, or yaw. There's a whole bunch of these get last something 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 reset methods inside the HRS. in EKF, and it's a timestamp, and it'll tell you when was the last reset. So, you know, the caller maintains a local copy of the last reset time, and if they ever, and then on every iteration, they check again and again, it has that timestamp change, and if it does, then you do something. You know, resets happen, you have to do something. And then inside of the copter attitude controllers and position controllers, we handle these jumps by moving the target. So this is really Leonard's work, but you know, say for example, there's been a position jump, like here, you know, in this little diagram here, you know, for example, suddenly the copter's position has moved a few meters to the right. We move the target. So in this case, you know, the vehicle was, say, trying to aim for a target 1 meter or so ahead of it. Suddenly the whole, you know, vehicle is moved a few meters to the right. So we move the target a few meters to the right as well. And, you know, it's a small point, but I just like to point out that to avoid a jump, you need the same amount of error before and afterwards. So if you get a position jump, that doesn't mean, oh, let's move the target to where the vehicle is now. That's not what we want. That would actually cause a twitch. Instead, you just need to make sure that the error before and after the jump is the same. So the vehicle's response is the same. Its heading, or sorry, its heading, its attitude is the same before and after the jump. Okay, then we get down to a couple of known issues. So if you look closely at the map during one of these transitions, you'll notice that there's a difference in behavior between when you move from non-GPS to GPS or the other way around. So when you're moving from a GPS environment to an external nav environment or non-GPS environment, there's no jump on the map because of all this jump avoidance work that we've done up above. The vehicle just smoothly moves, no jump. But going the other way around, it does jump. So yeah, if you set, for example, like in the example that Hammy gave earlier, you know, you've set your home position slightly off from where the vehicle really was. Then you fly the vehicle outside, it gets a GPS lock. Suddenly it knows exactly where it really is, and it will jump a few meters. The pilot won't necessarily see it, but on the map it will jump. And the place where this really causes trouble is if you're doing a mission. So in loiter mode, you don't notice. The vehicle doesn't move, the target was moved, so there's nothing bad happens at all. But in a waypoint mission, it does matter because you're going to a very specific latitude, longitude, and altitude target. So when it transitions, you can see the vehicle. You know, the vehicle may suddenly, you know, move left or right or whatever a few meters to get rid of that sudden position error. It shouldn't be a drastic, crazy, you know, lean over at 45-degree type response. It's sort of the standard response that you get to any kind of position error. So it should be a, you know, a gentle, controlled shift, but it will definitely shift. And then when you go to RTL later, you might find, as I mentioned earlier, that the vehicle comes back, but it lands away from where it actually took off. So that's a known issue. I don't really have a solution right now. I'm certainly open to suggestions on ways to fix that. Just a couple other little known issues. Right now, the vehicle, as far as I know, from my investigation, we do not handle velocity resets. And also the EKF doesn't provide an accessor to tell us about vertical velocity resets. So vertical position resets, we definitely get told about, but we don't get told about vertical velocity resets. Maybe that's because they always happen at the same time as the position resets. I'm not totally sure. I think what this means is that you may see a little bit of a jump in altitude when switching between sources. So yeah, just see a little question here from Alex Burka. So if you are using the example of a T265, which is constantly drifting over time, won't its innovations grow if the faucet is turned off? Yes, okay, great question. So the thing is that we are actually using the velocity innovations, so not the position innovations. So yeah, so maybe this is the point here. Maybe this is here, but velocity innovations, even if there's a little bit of drift, the innovations won't grow. They'll be sort of constant. So I think it's quite easy to use, I think, velocity innovations as a decider as to which sensor is good or bad. Position innovations would not be so good for a couple of reasons. One is that we might be constantly getting rid of that position offset, through this avoidance work here. So that, that would essentially negate the value. It would always appear to have a innovation of almost zero. Yeah, so velocity innovations are the ones that we're using. In particular, vertical velocity innovations are very good, especially with the T265, which has these crazy, T265 is awesome when it works. It's just got this weakness with vibration, which means that especially the vertical axis can go wonky if it hasn't been mounted properly. Okay, I guess I'll just move on. Yeah, this is just talking a little bit about simulation. So we also improved the Vicon simulator in CITL, which allows you to test these transitions quite easily. There's a wiki page again, of course, which you can refer to if you want to set this up. But it's pretty much the same as setting up a real vehicle. So you set your VISO type to 2, then you set up all of your little sources. And you have to set the serial 5 protocol to MAVLink 2. And then when you start sim vehicle, you have to tack on this bit at the end, the -a, UART equals sim Vicon, and then that will produce, simulated Vicon, which is going to be constantly feeding in, those vision position estimate and vision speed estimate messages to RDPilot, and then they'll get consumed in the regular way, just like on a real vehicle. But there's also been a bunch of extra parameters added. So, for example, you can add in a yaw offset, so that you can essentially simulate the camera's, the vehicle's pointing south when it's powered on. So there's a 180-degree, angle offset from the camera, and then you can test how that how our avoidance jump avoidance code deals with that, and etc. So yeah, this is very useful. I think you can add glitches in, a bunch of things like that. Okay, and yeah, the second to last slide is just about future plans. So we'd like to fill out the calculation of the velocity innovations a bit more. So we simply don't calculate them, or we don't make them available, I should say, to the Lua scripts for optical flow and wheel encoders. And if we had that, it would definitely allow the Lua scripts to be more confident in their making of decision, in their decision making. Also, as mentioned earlier, we'd like to add support for the switches to happen via MAVLink commands. Also like to build out some more Lua scripts. So we just got these 2 examples. Really would like to build a GPS plus optical flow example, which I think is probably going to be maybe the most common script that people really would like to use. We'd like to automatically align the external nav's heading to the HRS when the external nav is not the active source. So like I said, we're only doing that right now via an auxiliary switch. We should really do that automatically all the time. It should be a fairly simple change, but the next thing too, and this really fits in with the 4.1 beta release that's coming quite soon, is more demonstrations and videos of the system working with different combinations of sensors and in different situations. I've seen a couple of examples of other users and developers using it successfully, but definitely want more people testing it out. And if there's any issues, of course, I'm on standby to help overcome them. A great place actually to talk about this feature is in the Vision Projects channel in Discord. That's I'm usually there, and there's a bunch of other developers there as well with experience of the feature. And then maybe at some point we might want to transfer some of these logic that's currently in Lua scripts into C++. I think it's too early to do that. I think we're sort of still in the stage where we're discovering which inputs are important. Once we're much more confident that this is the logic that always works, we could transfer that potentially to C++. That would allow it to work on boards with less memory perhaps and less CPU power. So that's pretty much it. Last thing, I just want to thank some of my supporters who helped me with this project. So Droneability is a company here in Japan, and they were the ones who were really pushing for this feature. So Kitoko-san is their CEO, and he did the project management for this project. I've known him for years. He's also on, we do a lot of search and rescue work together as well. Kawamoto-san, he was doing software development of some of the Lua scripts. And he also works, he's a teacher at Drone Japan School here in Japan, of course. And Komiya-san is the guy who worked on the frame, and also he was the test pilot. So yeah, thanks very much to them, and also to Eames, who's been supporting my efforts for years. Thank you very much. Any other questions? Okay, well, thank you very much. And like I said, if you give this feature a try, and if I'd really love to hear feedback on whether it's worked or not worked, or what have you.
All right, fantastic. Thank you so much, Randy. That was absolutely brilliant. And it's a fantastic new feature, being able to do GPS, non-GPS navigation like that, and really nice demo videos. Much appreciated. So in the schedule we have up next, Patrick Pereira, or better known in our community as Patrick Electric, and he's be talking about Rust MAVLink. Now, Patrick, are you about ready to go?
Yep.
There you are.
I am ready to go.
Fantastic. All right. Well, I am just going to organize the recordings. Just switching on over the recording to the new person. Now I need to check. Can you just check if you can screen share? Do I need to give you host there?
No, I need
work
to
for you?
give permission here.
Do you got permission?
Not yet.
Okay, let me fix that up for you. Where are you? So you should have permission now.
Ah, yes.
Great. So, so Patrick's going to be talking to us today about Rust MAVLink, and you've got some very interesting psychedelic effects going on with the video effects there. That's great. So fantastic. Over to you, Patrick.
First, I tried to find the correct Chrome tab here, and I think I found it. Yes. So probably you're seeing it here now, right?
Yes, coming through fine.
Okay. So I'm going to talk about Rust MAVLink. To make it a bit fun, it's midnight here in Brazil, so I'm a bit tired, and I'm also sick, so my mind is not working 100%, but hopefully everything will go fine today. First, this is the topics that I'm going to talk about. Who am I? What is Rust? Why it's important to know about Rust? The language itself, I'll take some time to explain about the language, because if the language wasn't important, the library would not exist, because C++ or Python could provide the functionality that the Rust library or the Rust language provides. But I believe that Rust has a significant part in our development of critical applications and safe applications, safe in a way that it will not break. So as I said, my name is Patrick José Pereira. I'm an electronic engineer, also known as Patrick Electric at GitHub. I work actually right now at Blue Robotics, working with submarines and ROVs. I'm also a KDE contributor since 2016. And I work with drones and terrestrial vehicles in general, robots, since 2011. My first project was with a tilt rotor, like a B-22 Osprey. working with the embedded application, creating the fly stack from the ground. And since 2016, I collaborate with Autopilot, and since 2017 with the MAVLink organization. So what is Rust? First, as I said, I would like to put some time to talk about the language itself and the features behind it. And without doing so, it will be not clear the important for us as developers why Rust is important, why Rust MAVLink is a good library for us to write embedded applications to communicate with the vehicle, or creating desktop software, mobile software, or and even web front-end applications with MAVLink integration. So as I said, Rust is a programming language, but it's not just a programming language, it's also an entire ecosystem. When you have, as ecosystem, have its own release cycle, it does not depend of your operating system or your package manager of the operating system. Like if you probably have a really old Linux version that does not provide the latest version of your compiler, things like that. Rust has its own release cycle. So if you use Rust, you always will have the latest version, and everybody can walk together with the language and make it easy to have the same work and development between multiple computers. It has also its own package manager. So if you want to publish your binary or publish your library or install a program like bat or heap grab or search, you can use also Cargo. It also is the build system because it manages the dependencies of a project and builds your project as well. I will be in more details later. And also has its own documentation, learning material, code style. So it's entire development ecosystem where there is a standard defined and the people should follow the standard. It's not only as a code style, the documentation style, the tools that you use to provide this, and in all the documentation is also available in a single place where all libraries can be accessible there. And the same thing applies to the packages that you want to use, making it really easy to develop applications because as in Python or in other languages that have a package manager, it's really easy to fetch and use libraries of third parties. And also one of the most important things about Rust is the community. A friend of mine once said that if someone wants to find a programming language to start programming, then one of the first things that it should look for is the community. A community that helps you to learn, a community that provides you with the necessary information, and also a polite community with everybody. And the Rust community is really worried about making Rust as a language in the community as friendly as possible to everybody to code on it and help each other. So why it's important, why I'm talking here about Rust. And a language is like a tool. If it's the right tool for the right job, you are going to use it. Also, a tool can make your job easier or making your life in general easier. When you use a tool that can make your workflow faster or can save you time on the long term, being able to identify problems at compile time, almost all problems possible with memory leak or data share or data racing, things like that. It helps you to create really stable and reliable applications. And with the powerful of the libraries and package manager, making it possible to quickly develop a prototype or the application that we're looking for. And what I'm going to provide right now is how I started with Rust, because when someone starts talking about a new programming language, usually have a grain of salt, like, okay, it's a new programming language, as the others probably will not match C++, Python, or other like pretty standard language to software development. But Rust is getting really quick closer with a bunch of tools and really important libraries and incredible software practice and language architecture that makes development really easy. And after you start coding on it, in the end, you understand all the problems that you can find by coding in other languages. So the Rust started in 2015 with the 1.0 stable version. As you can see, this is the Stack Overflow survey about the most loved, dreaded, and wanted languages. Rust, the 2015 was in the 3rd place. In 2016 was in 1st place with almost 10% over Swift. And that goes on. In 2017, the same thing happens. Same thing happens again in 2018. Same thing happens again in 2019. And 2020, with almost 20% of like over TypeScript as the most loved language. So if a language gets for 5 years in a row, the most loved language, there is a reason behind it. And that's how I started to learn about the language. And after working for more or less 2 years, I think that's a really good alternative to create embedded applications, desktop applications in general. And I believe that it's a good alternative for us as developers. So I believe that as developers, as humans, we need to be safe, because humans can be wrong, can write software that's not reliable somehow, but not because they don't understand what they're doing, but by mistake. A human, it's unreliable when writing software. Of course, we have the review process that makes it harder to bugs and problems get measured in our code base. But the thing that we need to take care is the problems that we may face one day. So we need to be saved from ourselves. And there is a really important image that explains that. There is the desktop from David Barrow, and in the top it says it must be installed to write multi-threaded code, because writing multi-threaded code like in C++ or a language that does not provide data race conditions and things like that, it's really complicated, because you need to think about all problems that you can find. And as everybody knows in the industry, it's really complicated to write code that's reliable and really, how can I say that, in a way that will not have problems in the future, or bugs, or security for memory leaks and things like that. So Rust took all the history of the other languages, like C++ example, and tried to learn from their mistakes, or the problems that the language, as in the way that was designed, comes with. So in C++, the good practices are const correctness, as an example, don't expose private parts, don't leak memory, consistent code style. And also there is no default build system, no default documentation style, no default package manager, and also there is no code style in general. And that's a bit problematic, because when you work with multiple projects, multiple organizations, in the end, you need to learn 3 or 4 different build systems. You need to learn 2 or 3 different documentation backends. You need to understand different test engines, making the life as a developer a bit harder. And Rust took all these problems with all the other languages and tried to create architecture that makes sense, or it's like not make sense, but in a way that will not have problems to a developer. And the good practice will be forced by the compiler and also by the language itself in a way that was designed. So in Rust, if const correctness is a thing, all variables, when you define, they are const by default. So you don't use the const keyword, you use the mutability keyword as an example. Everything's private by default. So if you have libraries, if you have like namespace and structures, fields in the side structures, everything will be private by default. And only the things that are really necessary will be provided as public. And everything needs to be explicit for the developer. Also, there is for MAVLink, there is a really good approach that's called the borrow checker. It checks if a variable was borrowed or moved, and check if the same reference, the same pointer is used in multiple places. It checks if the pointer, the reference is mutable, because if you have like the same reference that is mutable in two different spaces, you have problems with data races. And these everything can be checked in compile time by the borrow checker system in Rust. So in the end, you find a bunch of memory problems in compile time, making almost impossible to develop softwares that are unsafe as in a normal day. Of course, there are things that the language will not detect, but it's really hard. And if you want to be unsafe, you can use the unsafe keyword, and inside there, the compiler will say, okay, I trust you that you know what you're doing, and I will not talk nothing about everything that you were putting here inside unsafe, but I trust you. So it's when you do unsafe code in Rust, it's really explicit that the code is unsafe. And when someone's looking to the code, reviewing the code, it will take like a keen eye on the code to make sure that this is really okay and this unsafe code should be safe for us. There is also the default language code style, the default build system, the default documentation style, and the documentation provider, the tools to build the documentation itself, and also the front end to visualize the documentation. Everything is provided by the community. And also with the language, a language is not like really important, like really interesting if you can't deploy your application in multiple architectures. Rust has, if I recall correctly, 81 targets in the tier 1 and tier 2. These targets in tier 1, you're guaranteed to work. And with tier 2, you're guaranteed to make it, to run it, like to build it, but it may not run as expected. But in general, I never found a problem with it. I also built for ARM in Arduino AVRs in general, and I never found a problem directly. And also there is the tier 3 targets. There are targets that are in development. These in general, they provided a standard library. So if you have a target in tier 1, and tier 2, and it's not bare metal, you provide the standard library, but of course you you may not use the standard library as an option because the language has features on it. It's like in C++ defines, but it's a bit more powerful. And with that, you can disable the standard library, disable features of your libraries that you're using in general. In Rust MAVLink, when you want to use a specific dialect, each dialect is a feature. So when you use the library in your project, you need to specify that you're using Rust MAVLink with the feature common or Ardopilot Mega, or with the SERD, SERD as a serializer. If you want to create JSONs, TOMs, XML from MAVLink messages. So to add a user target, it's really simple. It's RustUp, that is the installer of Rust, target add the target that you want to use, like ARM, Linux, GNU or Muzd, and to build just cargo build -- target, as simple as that. And you can see the examples for a Cortex M0 and a Raspberry. And now I'm going to talk about the language itself. This is a simple example of Rust. As you can see, you have the definition of the function main. You have the hello string variable, and you create a string object from a static string hello. And we have the print ln with hello string. As you can see, you have different types of prints. Here, this is like a pretty debug format, and this is the normal format if you want to print something. Also, if something is not mutable, as I said, our variables are const by default. So if you try to modify a const variable, the compiler will warn you that you're trying to modify a variable, and it says as a tip that you should consider changing this to a multiple, like mut hello string. If you want to read more information about this issue, there is also the rustc explain command that will provide error information about the error that we're facing. So as you can see, the errors are really friendly. And how do you, to understand your error that we're facing, the compiler is also providing information like how you can get more information about the problem that we're having here right now. And if you define the variable as mutable, you can modify the variable itself. Of course, if the type, since you're compiling the code, the compiler can choose the correct type that you want to use. If that's not possible, you can also provide a type hint to say, okay, this is this type. Or when you have like a map and you have to collect all the maps output, you can also you need to specify a type, because Rust will not understand what type that you want to transform. So the type itself is not necessary because the compiler knows it. So you don't need to be explicit about it. And also if you use tools in your IDE for the language, it will also provide all types that the compiler is looking for you. So for structure definitions is the same thing, not so different as C++. So define a structure, as you can see here, airplane attitude with row pitch in yaw. And with the attitude you just define the structure, and in theory you should print the structure. But that will not happen, because in Rust it has traits that's something closer to concept in the new C++ standard. So for that, it's saying that airplane attitude cannot be formatted with the default formatter. The trait standard format display is not implemented to airplane attitude. So to fix this issue, the only thing that we need to do is to implement the display, or in this case, the debug trait for the structure airplane attitude. And with that, we can print the message. Or of course, this is a bit unnecessary, because in Rust, you can generate code with macros and also with the keyword deriv. With that, Rust can generate code for you, and you can also generate code before your code starts compiling. In Rust, there is a step called build that first it will run a build.rs or a main.rs that will compile in Rust and will run. And when this run, it will generate Rust for when you want to compile your real code. In a way that's how the Rust MAVLink is generated. We have a build step. The build step builds itself. It parsed all the XML files. It generated all the files for each dialect. And with that, we build Rust MAVLink to be available in your application. So it's a really interesting approach where the language can build itself, or the program can build itself and generate the libraries necessary for its own files. And of course, there is also the normal debug. There is also the pre debug. So you can see the format is changed, but it's just for developers to understand and make it more friendly when debugging your application. And of course, you need to change your variable to mutable to change it, and you also can access the fields. But if your structure is available inside the library or inside a namespace, in theory, you should not be allowed to access it, because the structure inside the namespace is private. If we include something in a model, it will also be private. So everything is private by default. Nothing is available. So if you have, like in C++, you have a header inside a header, and you include this header, is also be available for you. And that's a bit problematic, because you are including things that you don't want. It's hard as developer to find everything that needs to have all the includes for a file. So in Rust, it is really easy, because everything will be private by default. So you need to be explicit when something is public. So for that, we define the structure as public. But the field inside the structure is also private. because you can have like fields inside your structure that are necessary for your functions or for your traits to work. And there are fields that may be accessible to the user. So you need to do this decision to show what is available or not for the programmer. So it is a way to communicate to when creating the API to the developer, like, don't do that, use this function if you want to create, or you enforce the idea to how to use API in the way that you use your software architecture. So when you define out fields public, you can modify and do everything that you want. So as an example here, this is about the borrow check. Here you have a string variable, and the string variable has a reference to array 1, and you can print array 1. For now, everything is okay. But if you want to change, you have a multiple reference. Like if you have a pointer, you want to create a multiple pointer, as an example, Rust will not allow it because you define it first that this is not mutable. And now we want to turn it mutable, and the compiler will not allow you to do such thing. But you can turn the string itself mutable. There is also the problem where you can't have two mutable references to the same for the same object. The reason behind that is that Rust has restrictions to prevent data race. So at compile time, it's able to identify when something when something is unsafe, when you have or don't have threads, and say, okay, what you're doing here is not safe. You'll not compile, and that's not okay. So this is necessary if you want to create code that is safe, because this will take care for any data race condition. Because two or more pointers can access the same data at the same time. And you can have one that can be mutable. But when you have multiple reference for the same thing, you are going to have problems with the data race. And everything is checked at compile time. So making the code more reliable. It's really hard to have a Rust code that compiles and have problems. Usually the only problems that you're going to have is the problems that you said that you are going to accept it. So now I'm going to get inside talking about MAVLink, how to use MAVLink with Rust. So this is a bit of example of Rust MAVLink. First, you create a MAVLink connection. You need to specify the type of the connection, like UDP in, UDP out. You can also not use the MAVLink connection. You can use anything that implements the trait IO. So if you have a file or you're receiving data via UDP, TCP, or anything, the only thing that needs to have access is to the concept. So if you have a IO device or IO structure that implements the concept IO, Rust MAVLink should work. But in this case, as you can see, we are creating a connection that uses the MAVLink autopilot messages. And with that, we are setting the connection with MAVLink version v1. By default, in Rust MAVLink, the version is version 2. And with that, we create our ARC or a smart pointer. ARC stands for Atomic Reference Counter, because we are dealing now with threads. Rust MAVLink does not, when you try to decode data, it will lock your IO device until it finishes a message. So right now it's necessary to have threads if you have an endpoint receiving data. Otherwise, you're going to lock the decoding method. I'm trying to work on it to fix this issue, and probably it should be fixed soon. So with that, we create a atomic reference counter from Mavicon. And we clone this atomic counter, or this smart pointer, to the thread. Doing so, we have two smart pointers that are atomics and are shared between two threads. And this vehicle can send by default the heartbeat message. And if checking if the answer is okay, it waits for 1 second to repeat the message. Otherwise, we'll print what's going on. And after that, there is a loop where you can receive the message. So you check type of message. You will, by default, you receive a tube with the header and the message itself. The header, as a MAVLink header, contains information about the vehicle, and the message is a MAVLink message. If something goes wrong, if you don't receive the message, you can also print what's going on. And when you receive a message, if you run the example, you run MAVLink, you are going to have as output, like received common raw emu data in the data of the message. Right now we use enums. There is something wrong with the presentation because I had an example with enum, but imagine enum as something that can contains data. So you can have a normal enum, and you can also have an enum that contains data. In this case, you have a common enumerator. That's a common MAVLink message. Inside the common MAVLink message, you have the common MAVLink message. In this case, you have the raw emu. If the raw emu, you have the raw emu data that is structure that defines the MAVLink message. You also have the ArduPilot message. As said in the previous slide, well, I was using ArduPilot Mega as an example. And with that, there is the scene state. This is ArduPilot Mega message. And with that, you have the ArduPilot, the scene state output of the message itself. ResMAVLink, as I said, has support to SARD. SARD is the common library for serialization. So if you want to create JSONs from it, or if you want to create XML, TOM, or any data that can be serializable, SARD will do the job for you. And this is really handy when you need to create applications that are for web, or just want to have the data in a available, in a friendly way to be accessible. And there is also for embedded applications. So in this example, I'm using the Cortex M0. In the Cortex M0, I'm creating the PA2 and PA3, that is the TX and the RX pin. And I'm using the GPIO-A in configuring it to use as a serial port. And with the serial port created, as you can see in the middle of the file, it's necessary to configure the user that wants to use, the pins that you want to use, the baud rate, clocks. So as a normal bare metal development. And you can also split the TX and RX pins and have two different objects to reference the same pins. And to create, after that, you create a MAVLink header and a MAVLink heartbeat message. Inside the loop, the only thing that you need to do is to write a versioning message that is sent via TX that you're receiving as a multiple reference. So using the IO device to write the header in the heartbeat message. And if everything goes fine, you toggle the LED, and you'll also take a couple of seconds to sleep. And to create the MAVLink message is really simple. You just define a MAVLink header. As in the example, a MAVLink message, in this case, a common message, a heartbeat. It can be a bit noisy because you need to define all the fields, but same thing applies mostly for all languages. You can also create functions that abstract that for you. This type system is really strong, so it will not allow you to put something that MAV type does not support, or something that is not inside your autopilot enumerator in base model in system status. So Rust has such a strong type system that is really hard for you to write code that's wrong, like trying to send something that does not exist inside the MAVLink standard. Since Rust MAVLink follows the XML description of the MAVLink message, it will generate all the code related to it. So if you send something that does not follow the standard, Rust will complain about it, saying that, okay, this field that I'm trying to use does not follow the rules that you described. But this is handled by the language itself. If something may be possible to fail, you have like a result or optional return types. And with that, we can understand what's going on, what is the problem. And it's really interesting work on it because I was able to find one or two problems in the specification of the MAVLink implementation inside Autopilot. There are issues created about that. But it's important to see that a language is really helpful. And since it's strong with type system, it's really easy to find such problems with it if something does not comply with the MAVLink specification. So about the future of the Rust MAVLink, something that does not have it right now is async support. You have to control everything by threads. There is also no blocking parser. When you try to receive something, it blocks until you receive a MAVLink message. Also, there is no full support to MAVLink signatory validation. We do have MAVLink signatory, but there is no validation for now. And also the MAVLink version, it should be decided at compile time and not runtime. Same thing applies to the version and also for the dialect. Things that I would like to complement is that I did some examples, some tasks with size. And most of my tasks, I got a smaller memory footprint with Rust, working with the Cortex M0 and also with AVR. For both like serial, sending a simple heartbeat, difference can be, if I'm not mistaken, it was 700 bytes, like 1.4 kilobytes for Arduino example using MAVLink C library, and around 800, sorry, it was the only difference to 2 kilobytes. In the end, the serial implementation, only the serial implementation was only a few of 400 bytes, but the difference between the Rust implementation and the C++ implementation in AVR or in a Cortex M0, it goes over 2 kilobytes. So it's really interesting as a low memory footprint. I got in some problems with the presentation. I don't know, some slides did not appear. But when coding with embedded application, since the type system is really strong, it will identify when you're trying to do a wrong register configuration, or trying to register a pin with the wrong register. When try to put, like, you have a pin that does not support serial and try to configure serial in this pin. So the compiler will detect everything in compile time, and that's really interesting because it saves time. And when you work with embedded applications, if you check the STM, the Cortex M0 documentation for Rust, you can see that you don't need to check a look on the datasheet. Everything is provided in the documentation itself. I was a bit fast in the slides. I was unable to talk a lot about Rust MAVLink because it's a bit complex and I need to explain everything related to the language itself. But it's a good alternative if you want to develop, as I said, applications, desktop applications, or bare metal applications, and to create reliable code in general. I do believe that in the future, more and more applications will be writing Rust. Probably in robotic systems, it's getting more and more attention. And for MAVLink examples, you can check MAVLink to Rust. That is a library or a program that's read MAVLink and provides MAVLink as a REST API, so you can control the RLV via post methods or WebSockets. So you can receive and talk via WebSockets with your vehicle if you want, making it really friendly to communicate with the vehicle without having the MAVLink library itself. You'll only communicate via JSONs that describes the protocol. And also the MAVLink camera manager that I'm working on that has JStreamer integration, Rust, and uses the MAVLink protocol via the ground station to provide information about cameras, controlling, etc. For now, it's really reliable and without much problems as a language. And that's all that I want to say. Thanks.
Fantastic. So thank you very much, Patrick. Really appreciate that. And it looks like Rust provides a really nicely structured way of interacting with MAVLink. So do we have any questions off the floor? Everyone's gone very quiet. Very quiet there. So I think I was actually wondering about with the multiple mutable references, I was sort of in the back of my mind was, should we at some point think about implementing some types of things like drivers and things in Autopilot in Rust? Because, there's been a lot of projects that are looking at that possibility. If you can't have multiple mutable references, that's a very common pattern we have. Can you embed a mutex inside the reference so that you can have multiple mutable references, but it uses the mutex to make it memory safe?
Yes, that's how you do it. So when you have like a static variable, in theory, a static variable is really dangerous. So for that, if you have a static variable, you need to define the static variable as an arc, atomic reference counter. Inside the atomic reference counter, you need to put a mutex to make it sure that you don't have problems between threads. Right, great. Okay, really good. Well, I'm actually looking forward to having a bit of a go with Rust with MAVLink. It looks like a very nice syntax that you've developed. And so it looks really expressive. So I might have a go at that soon. So thank you very much. If there's no more questions, then this is actually the end of the first session. So I'll just check if there's any questions off the YouTube feed. Now, okay, we don't seem to have any questions at the moment off the YouTube feed. So
one question there, I guess, from Alex Burka about where the slides are, in case.
Yes, so Patrick, could you possibly send me a link to your slides and I will put them up as a link inside the schedule so that everyone can access the slides? Is that possible?
Yes, totally. I will send it right now.
Great, great. Just send me that on Discord and I'll pop that up in the schedule immediately afterwards. So thank you very much, Patrick. Really appreciate that talk. And so that brings us to the end of the first session of the conference. So the next talk that we have for today in Australian time is 7 p.m. this evening, which means that's another 5.5 hours from now, just under 5.5 hours to the start of the next session. And the idea is that this evening session is going to match with slightly better time zone for European speakers. And so the next speaker we have lined up is Samuel Tabor, giving a soaring update at 7 p.m. this evening from Scotland. So we'll have a break now and time to go out and get a late lunch if you're in Australia, and otherwise some dinner or breakfast wherever you are in the world. Feel free to hang out and chat in the chat rooms for the conference on Discord, and also join the voice channels on Discord. So I'll be shutting down the Zoom call now, and I'll also start processing some of the videos, and I hope to get up at least draft versions of the videos up on our YouTube channel quite quickly. And then they'll be refined later when Louis starts doing some work on them. But thank you all. Thank you all the speakers from this morning. So Paul and Randy and Patrick, much appreciate your fantastic presentations. And I didn't miss out anyone, did I? We got that right. So,
only yourself.
And I'm sorry. Oh, myself. Yep. I'm not going to thank myself. And so look forward to talking to you all later today for the evening sessions. And there's only 2 talks, so 2 hours of talks in the evening session. So see you all back here in a bit over 5 hours time, and for more conference goodness. All right, and thanks everyone for our audience on the live stream on YouTube as well. Thanks everyone.
Bye-bye, people.
Bye everyone.
See you later.